morning. We're starting today hour late, so it's a little bit shorter than usual. That's right. So last lecture we have seen or developed the base design, or how to calculate the parameters. Today we'll be looking at how to optimize that design and why we would like to optimize. Okay? So if we use simply the classical equation what we discussed last lecture and found the base design, use finite element to do performance evaluation, we don't know whether that's the best design possible or not, right? For various criteria, we don't know where we are. We could be obtaining something of a local optimum design in a design plan. We don't know where we are. But if we could do a optimization, or if we could use some kind of optimization technique to design it, we could ensure to find a global optimum for that design, okay, in a design space. So that's why we would like to do optimization. Now, first, that's why in this first part, we'll be looking at what's the basic process of optimization. And we'll be looking at also what is the multi-physics and multi-objective optimization means, and like what are the advanced processes. Okay? So nowadays the optimization is becoming more and more of application based. Okay? So the application decides what is your criteria that you want to optimize. In our case, it is EV. We could take the Freedom Car 2020 spec that we talked about in our first lecture as our optimization criteria. Okay? For example, it doesn't have to be that. For example, that could be our criteria. Or that determines our objective. For example, you can see that we want an efficiency of greater than 95%. So my optimization goal could be an efficiency of 95% or higher. And similarly, we could consider weight and size as our optimization goal, or cost. Okay? All these could be our optimization goals. So first we will, as you can see, we could have more than one objective or goal, so that's why it's called a multi-objective optimization. Okay? And we do try to optimize all this together. And from our previous discussion, we know that this optimization, all these parameters, efficiency or size and weight, even cost, all are interlinked to each other. Okay? Therefore, and it's a kind of trade-off between each other as well. And then on top of that, we have the limit, such as thermal limit or mechanical limit that we talked about in last lecture. And then the design must be also manufacturable. So these all need to be considered during this optimization process. Here you can see a very general process for any electric machine. Okay, this design optimization method. We could look at type and topologies, material and dimensions. We can optimize it just for electromagnetic performance, okay? Or we could consider all three together, electromagnetic, structure, and thermal in our optimization. If we want to be even more if we want to make it even more complicated, we can in fact do it as a system level optimization, that we include in optimization even inverter and control, part of that optimization process. Okay? Or the whole process or application would also be influencing that design optimization. And then this design, once from this we will get some feasible designs, and the method that we use for optimizing these base designs could be model based, could be algorithm based, or could be some strategies. Okay, so usually the model based ones are kind of deterministic method, so they may not guarantee you that we arrive at that global optimum design. Okay, and also the model need to be very accurate. Only then you can use the simply model based method. So that's why the most popular one is the algorithm based. So we could use some intelligent algorithm to optimize it. Algorithms such as genetic algorithm, AI based. We could use the particle swamp optimization. We could use even like a more advanced data driven machine learning based optimization. Okay? It could be, you could make it any, you could use any sort of advanced algorithm for optimization. Okay? And that last one is that kind of strategy based, especially if we are doing the multidisciplinary, like if you want to include it as a system level optimization. You are including your inverter, controller, you are including all three things, the electromagnetic, structural, means mechanical, and thermal. If we are including all this, then it could be some kind of strategy that we develop, because algorithm-based method may not have enough computational power to handle everything together. Okay, so in that case, we look for simplification or strategies that we can apply. So the example that we'll be talking about mostly is algorithm-based. Okay, that's what we are using. Let's consider the traction motors, PMSM motors, as a high performance machine. Okay. So design criteria or objectives could be, as I said, based on your application. For traction, obviously, we would like very high efficiency, low torque ripple, so that we can have smooth run. And high torque density in size, high power factor, which will influence efficiency as well. Cost is need to be considered so that it's affordable, and it still need to be robust enough mechanically. We don't want any maintenance if possible, and it must be easy to manufacture, and if possible it should have also fault tolerance. Okay, so any of these or all of these could be your criteria, okay, based on what is your preference for your application. And sometimes not all of them together can be achieved as well. Okay, sometimes if you are achieving high efficiency, very high efficiency, maybe you have to then compromise in cost. You may not get low cost. The cost will be high. Okay, so it may not be possible to achieve everything together. Another example of that sort of trade-off is that you may not, when you are trying to reduce torque ripple, you may be also reducing the average torque. So that means it is compromising on torque density. Okay, so that's sometimes that's why getting 2 or 3 of them together may or may not be feasible depending on the requirement. Next, once we have decided our criteria or objective, the next is to select, right? Or because we could have also different options. For example, under material, although most commonly used is silicon iron or known as electrical steel. So this is what is almost in all electric machines we use, right? But then if you want high mechanical robustness, for example, very high speed design, so that rotor can withstand very high mechanical stress, then you may want to use something that has a much higher yield constant. Okay, so then in that case it could be cobalt iron could be an option. But if we use cobalt iron, obviously cost may go up. Okay, so it's a compromise. We could also use soft magnetic core SMC, but then SMC has a problem with manufacturability. Okay, so when you design it, you must also consider whether it will be easy to manufacture or not if we are using SMC. And SMC offers a lighter core, low core loss, but lower magnetic saturation. Okay, so compromising it. And then there are also new type of material coming in amorphous, which is like could have very high flux density, but light, but they are not easily available. Okay, so sourcing them would be an issue. Similarly, dual phase material. The dual phase material is such that you could so part of this material can become non-magnetic and other part can remain magnetic. So this dual phase material could be very useful while designing the either IPMSM or the synchronous reluctance machine. So in synchronous reluctance and IPM machine, this part is usually highly saturated. Okay, or in this to make this highly saturated, we keep this grease very thin, right? And this saturation happens actually by leakage flux, because most of the flux will be leaking between this pole and the next pole here, okay? And that's what makes this part highly saturated. Now, so we are wasting some of the flux, magnetic flux here. Okay, but it's necessary for IPMSM, and it is also necessary for the synchronous reluctance machine to have the thin bridges to improve saliency. But if we could use 12-phase material, this part of the material we can make non-magnetic, okay, and the rest is magnetic. Okay, so we especially in IPMSM, we are not going to waste your magnet flux there by making it saturated. So there is, and then well-phase materials also very will be useful for synchronous reluctance. And my understanding is that this material is being developed by GE, especially for synchronous reluctance machine in EV applications. But currently it's not commercially available. Okay, but it may come, and if it comes, it could become a game changer for machine like PMSM and synchronous reluctance. Then, so that's your choice of material for core, okay, stator core and rotor core. Then, in case of magnet motor, obviously our main choice is always a niobidium, right? but sometimes we may have to opt for Senko, cerium cobalt magnet, but then again it's a compromise on cost, whereas they are very good for robustness. Another option, this Elnico, is for the new type of PM machine that has been proposed, where you can switch on and off the flux, so you can demagnetize the magnet and again remagnetize through control. Okay, so that is can be done only one magnet like Elnico, but of course you will be compromising on the torque and power density. So then even ferrite has been proposed to use with the traction motor, but again, as we know, you will be compromising in density. You will also be compromising maybe in the fault tolerance, because ferrite can demagnetize easily. So design may need special consideration during optimization. If you are using ferrite, how can we improve torque density, and how can you make it magnetically robust? Okay, so that would become your design criteria if you are using ferrite. But you can then get a very cheap motor, because ferrite will be the cheapest magnet material. Some people are proposing to even, in fact, combine ferrite and niobium. So this type of magnet structure. So this part is usually demagnetized easily if you use ferrite. So they are proposing to use two separate pieces of magnets. So this vertical part to be niobium and the boron, whereas this part to be ferrite. So they call it a hybrid magnet motor. Okay, but it's actually IPMSF, just using combination of niobium and ferrite. Or the new magnet material that we have talked about before, that doesn't use rare earth material, that magnesium-based or iron-based magnet material. So instead of ferrite, we could also think of using those new magnet material in here and reducing the amount of rare earth magnet in the design by choice of those two. So those would be some new design that can be explored as a research project. Okay, and for winding, obvious source is copper, but then aluminum has also been proposed, because aluminum can make the motor lighter, right? So for aerospace, weight is more important. So they are proposing, why not use aluminum instead of copper? But of course, it will be again compromising on your current density of aluminum. There is even been proposal of developing carbon nanotubes for winding. Okay, but again, they are not commercialized; they are just research proposals. I haven't put this, but there is also, in fact, a proposal to use superconductors. Okay, especially for the wind generators, direct drive wind generators, okay, to use superconductor. And that will make the generators very, very, compared to a conventional direct drive permanent magnet generator or conventional synchronous generator, very, very small if you use superconductors. But the superconductor means you have to use cryogenic coolant, right? Because they need you must maintain the temperature at a very low value, so that cooling becomes a big complex thing. And next is the windings. We could choose what type of winding to use, whether to use distributed or concentrated, right? We talked about whether to use double layer or single layer, whether to use full pitch or short pitch, or whether to use like hairpin type winding. Okay, so these are your choice, and this choice could even become part of your optimization routine. You may try to see if the same rotor, but if I use a distributed winding, how its performance, or if I use concentrated winding, how it is performance, which one I should prefer, right? Which will give me the best option for to obtain my objectives. So that this choice could also be part of optimization. Okay? And then the rotor geometry. For IPMSM, we have so many different types, right? So here you are seeing a few that we discussed previously. V-type, double V-type, conventional flat type, double layer flat type, spoke type, or SPM. Okay? So these are our options. And out of these, we could check each one of them during optimization to see which one will be best suitable for achieving the objective. Okay? Now, when we do optimization, what exactly we are going to do, right? Other than this selection of various type and topologies, we will also in fact going to change various geometrical parameters, right? And so that this is what is called geometry optimization. So if you want to optimize the geometry, then we have to in fact assign all these dimensional parameters as variable to our optimization routine. Okay? So making the dimensional parameter variable is called parameterization of the geometry. Okay, so that's you are seeing here. For just take the case of a SPM motor, which is very simple. So remember we call this LM here. There in this figure it is showing as MTH. That means magnet thickness or magnet length. LM. This is one of the most important parameter, right? So this LM or MTH in this figure is a variable. Okay, it's a variable, and we can make it bigger or smaller by doing optimization, right? If it is a variable. Similarly, the angle. This is the magnet is making an angle here, right? This alpha P shown as the angle. This angle we can make it bigger or smaller by optimization. So this is a very simple example of geometry optimization. Okay. Similarly, for the stator part also we could vary these various parameters. This is the outer diameter of the stator. This is yoke width. Remember this, the thickness of this actually can vary with pole numbers. So that yoke thickness, tooth width, tooth height, slot, similarly slot width and slot height here. They are some of the parameters. If you look at it like a kind of a geometrical object, they will be depend on each other. Okay, so we could have like tens of means up to 20, 30 parameters here if we try to define each and every dimension. But many of them will be dependent on others. Okay, for example, this rotor outer diameter and your tooth width and slot width, they depend on each other, right? If you make it bigger, you will have more space for them. So, considering this as a geometrical objective, dependent parameters can be separated out, and you can simply select only the independent geometrical parameter for your optimization and make it the number of variables little bit less. If you keep all of them, it becomes like a numerical problem, right? A very large number of parameter optimization also may not be able to handle. Okay, so that's geometrical parameterization is the first step that you need to do in your optimization process. And yes.
Can you mark north and south pole with a double V-type shape?
So in north, so this is still, all of them could be north pole here. Okay, they will be like this. All right, double V shape, and the other pole here will be the opposite of it. This is, you are seeing a part of it. Okay, there will be another here. There will be opposite direction. So this is, if we call north, then the other one will be south. So here it will be south if you have 4 pole. Okay. Yes, this will be always like that. Okay, north, south, north, south. So the next pole is always opposite of that, whatever the first one is. The adjacent is opposite. Okay. So yeah, the magnetization direction also you have to define in your parameterization process. So spoke type magnetization direction is this, right? So next one will be opposite, that, and so on. You cannot put 5. It has to be always even number, right? Because your pole numbers can always be even only. You cannot have odd. Okay? If you have an odd number, then that odd numbered one, if you have 5 pole, let's say, the 5th one is not going to contribute anything. It will be simply like your interpole or some other things. It is not going to contribute to your torque production. Okay? Remember, this is why we have north-south chart is coming from your first postulate, right? D of B is 0. From there, actually, this comes. So it's always your magnet poles are even number. There will be, if you have a north, you must have a south. You cannot have a single pole. Okay? So
south poles are the opposite side of the moon, the back side of the moon.
it does not need to be. So if we have, let's look at the our previous lectures. Let's go here, right? So if you see, this is your north pole, this is your south pole, right? This is your north pole, this is your south pole.
They both are different magnets.
They are?
Different magnets.
Yeah, they are different pieces of magnet.
I'm talking about south of the one magnet. There are other
Yeah, okay, so if you're talking about that way, so if this is, let's say this is your north, this is your south. In the other case, this is your north, this is your south. Okay, that's how it is. Alright, that's how you define it. So magnetization direction tells you which direction the flux is going to come out. So that is your north. Right? So that's how you have to define it. Okay? So once we have done our geometric parameterization, now which type of optimization technique to choose, right? So we could do that deterministic type of algorithm, but then usually we cannot guarantee that we will see that global optimum. We may end up local optimum and we may have but it will be quick. Okay? And the base base design that we have used by applying the sizing equation is kind of inverse problem. Okay, because you have a set of objective, from there you have calculated out what will be your geometry. So it's kind of like inverse problem. So again, that's not going to help you in optimization. So mostly the that's why the stochastic algorithms such as genetic algorithm or genetic or PSO, this particle swap, or even data-driven machine learning type of optimization algorithms are being proposed. There are lots and lots of optimization algorithms, but usually genetic and PSOs are considered to be the most suitable for machine optimization. The data-driven ML has only just been started, so I can't comment whether they're good or not yet. Okay? So if you are thinking about new research PhD projects, so that could be a good way to look into. Okay? Whether machine learning can be applied for this geometry optimization. Okay? Whether it brings any advantage, I don't know yet, okay? Because it's just being started. Whereas genetic and PSO has been applied for many, many group has applied it, and both seems to work quite good. Although genetic algorithm is being preferred often, mainly because in the geometry optimization we have limited number of parameters, geometrical parameters, and GA or genetic algorithm seems to work better or more efficient numerically compared to PSO. So that's why the GA is used quite widely for machine design optimization. Okay? So we apply one of those, and then we will get a Pareto front of areas design that is fulfilling our objective, and then from there we have to select, right, which design. Because many of the design may satisfy our objectives. So that is, then you have to actually, out of those design you have to actually sort out. But to sort out, you need to evaluate their performance, right, of each design that you are getting. You have to evaluate them. So to evaluate, you could use analytical model, or we could use finite element. Okay, so analytical model is usually quite quick, but as we know, analytical model doesn't consider saturation leakage, so accuracy could be low, but it's simple. But if we use FE, it usually gives very high accuracy and good, especially good FE if you have very relatively complex geometry in your design. Okay, but it takes time. Okay, because for example, let's take the case of a genetic algorithm. In your first generation, you could have hundreds of designs. Okay, and finite element need to analyze hundreds of this design to calculate our flux density, calculate our torque, calculate our efficiency, compare them, and then give you, okay, this is the best design. Okay, so that takes time. And that's why FE-based evaluation is time consuming. And it may also need quite large computational resource. Okay, you will need at least a workstation, as I mentioned earlier. Okay, we need at least a workstation. You may not need supercomputer, but you need a workstation. The normal just laptops, they can do it, but they could take you weeks to give you a result. Okay, but the workstation may take you 3 days to get a result. That's the difference. Okay. And how complex your geometry, that also will affect your time, computational time. Now here you're seeing an example that we did. So how we did is like, in this case you are showing, because it's an example, we're seeing the two objectives here, cost minimization and efficiency maximization. Okay? And the constraint that we use in our case is we wanted to have, because it was a traction type application, so we wanted to have a wide constant power speed range. So how do we evaluate constant power speed range? If our characteristic current is close to the rated current. Okay, so this is a per unit value. So it's 95% or 105% of the rated current. So characteristic current should be of this value, and characteristic current is coming from your PM flux linkage and D axis inductance, right? So these two parameters, as we are changing geometry, changing various things, these two are varying. But I am putting the constraint that I must have the ratio always within this range. Okay. Then I may want to, in this application actually we were trying to evaluate the same rotor design for both concentrated winding, fractional slot concentrated winding, FSCW, and distributed winding. So we put two different torque ripple. For distributed winding, usually torque ripple is very high, so we give a higher constraint, 20% less than. But for fractional slot, we get much better or much smaller torque ripple. So our constraint here is only 5%. We want even lower than 5%. Okay. Then we have also put for current or voltage THD, demagnetization not to go below 30% of BR, and the stator tooth, as I said, is the highly saturated area, so we did not want that saturation to go above 1.8 Tesla. Because we are using normal silicon iron or electrical steel. Okay, for electrical steel, usually 1.8, 1.9, maybe 2 is the highest saturation that you can find. So that's constraints, these are constraints, this is my objective, and then how do we do? So first step is initialization. So initialization is you have your base design, so you parameterize that model, FE model, FE geometry, and then set your design variables, like from those dimensional parameters. And then also you define your objective and constraints, which are shown here for this particular example. And with that, you generate your first generation for a genetic algorithm. Okay, it could be up to hundreds of designs. So it depends on how many you can set that up. Okay, how many individual design you want to generate as a first generation. And then those first generation designs need to be evaluated, right, for various things. So that's the kind of the cost function for optimization, and it is this evaluation of cost function happens in FEA, finite element. So after initialization, that's why it goes to finite elements. So the interface between your algorithm and finite element is done through a Python program. So that we can automate this process. If you do not automate, then you have to get them out, then put them back in the MATLAB. Maybe your algorithm is in MATLAB, so it becomes manual. And obviously, it is, if you are talking about hundreds of designs, it doesn't like practical. Okay, it's not practical. So making it automated is best. So it will run by itself. Okay, it goes to FE, check all this, see whether it is satisfying or not. If it is satisfied, then it gives you the second generation. The second generation, so this runs in MATLAB. The genetic algorithm part runs in MATLAB, or sometimes in some I think some FE package they allow they have inbuilt algorithms as well. For example, NSYS has some GA-based algorithm for optimization, but they may not be very like advanced. Okay, they may do some basic things. So for basic things, you could use inbuilt FEA package optimization if they have it. Okay, if not, you develop your own, and that development usually happens outside of FE. So in our case, we did it in MATLAB, and then link the MATLAB to the finite element through the Python program. Okay. So the second generation, again, it will be going back to FE. Okay, and then we'll keep checking and giving you or storing the designs that is satisfying the criteria, and with that you will get a Pareto form. So all these dots that you are seeing here is actually a design, okay, actually a PMSF design, right? And you can see in this case it's actually, we have done many things. So this figure is showing saliency versus efficiency. We also have a figure like this for cost and efficiency. Okay, we have many such Pareto forms for different criteria. So this one was showing saliency and efficiency, and we want higher saliency so that we can get more reluctance torque, and obviously we want high efficiency, right? So something which is in this direction is good, right? Something, the design that are in this direction is good. So after, so for here you are seeing same example case as I said we did for FSCW and DW often for different rotor topologies. Okay, V-type, double V-type, flat type, and each of these design went through that process. Okay, it's a big, it's going to take a long time, but after all this done, you get those Pareto forms. Okay. In the next slide, you can see after all this how the Pareto form is coming up for these various geometries. Okay, cost versus efficiency. This figure, but we have again many different ones as well. Like we have torque ripple versus torque, we have saliency versus efficiency, saliency versus cost, efficiency versus torque, and etc. Okay, we could do many different things, many different Pareto forms. So in this design, our objective was to find which type of the rotor performs best with a fractional slot concentrated winding. Okay, so you can see here in this example, so we want low cost and we want high efficiency. So efficiency shown here is one inverse of the efficiency. Okay, I don't know why this is done by a student. I don't know why he selected like this. Maybe it appears better, the figure, that's why he did it as a 1 over efficiency. Okay, so that means higher efficiency means lower 1 over efficiency, right? So we want our design to be in this side. So if you look at this Pareto front, you can see that V type, the yellow one, and the grid spoke type appears to be good, right? Low cost and high efficiency. In case of fractional slot machine, whereas same rotor, but when we did it for a distributed winding type, it's a different result. Okay, flat type is still, V type is still performing well, but the next one is actually double V type, which has given you the higher efficiency and lower cost. Okay, and in this case, we kept the constraint of characteristic current to be within this range, as I mentioned earlier, because we still wanted to have the wide flux wicket. So you can see this is so many designs, right? And then you have to select some of them as your prototype. So that is again a refinement process. After you selected, let's say I selected from here a few designs, and then you can redo that optimization for those smaller number of designs to find 1 or 2 designs that you want to build. Okay, you don't want to build hundreds of them, right? So you want to, then you do a refined process of these few designs, refine optimization to find out one or two that you want to build. Okay? So when we are doing the same thing, the spoke type and V type or the fractionless slot, we found that okay, spoke type and V type gives us the best efficiency and lowest cost. But we also found that the spoke type gives us high torque, but compared to V-shape, but V-shape gives you low torque ripple. Okay, torque ripple was lower in this machine. So we decided to have another objective. Because one problem, as I mentioned, if you try to reduce torque ripple, usually this average torque becomes also lower. So we said, can we find a design that can give me the same high average torque, but torque ripple lower as V-type? Okay, and that means if we can combine these two designs. So that has actually lead us to this new design which I was talking about, Y-type. We call it Y-type. Okay, so how this idea came about is actually completely by this optimization process. You can see he was changing from spoke type to V type and was checking how is the torque ripple and how is the average torque. Okay, and then he found that at certain point the criterias are met. We get the high average torque and we get the minimum torque ripple, and that becomes his new rotor topology. Okay, so this shows you how the optimization can even lead you to something new completely that you did not even think about before. Okay, then obviously we built it, we tested it, and experimentally proven that it works as predicted by this optimization process, and we in fact patented it because this Y-type hasn't been done by anybody else. Okay, so that's one of our patents. Yes.
What is the VAR6 that is increasing?
This is the P angle, the angle. Okay, this P angle, this P angle. Okay, this angle. So you are changing this angle, so when this angle becomes 0, it becomes spoke type.
When the angle is increasing, the overall value of the magnet is very constant, or it is?
Oh, we are keeping it same volume. Okay, because magnet volume we want, because that depends on your cost, right? Magnet volume determines also your cost. So we try to get the same cost, right? But we also wanted to minimize cost. So we kept the magnet volume same as it is changing. Okay, so that's why the geometry changes. Okay,
when the spoke type is when we use spoke type more, that means your motor will behave more like spoke type.
Yes. So the higher the spoke region, it will behave more and more like spoke type, right? So there is an optimum like portion of spoke and Y, which will give you that highest torque and lowest ripple. Okay, so that's come out from the optimization routine. Okay, that how big the spoke type need to be, how should be the V type. As you have seen here, so you can see there, the spoke type portion of them may not be 50-50. Okay, it's some other percentage. Okay, so the other thing is that you don't always need to find new designs, right? It's not necessary. Sometimes you may just want to improve something on your existing design. So we designed a V-type motor for a concentrated winding, I think around 2010-11. At that time we did not optimize it because at that time we just simply wanted to check whether RPM rotor can work with concentrated winding. Okay, that was our purpose. So we did not optimize it. So we have this design but without any optimization. And then we passed this design through this optimization routine and found that if we optimize the design, we can increase efficiency by 11%. Okay? We can increase the torque density by 23%, so make it smaller, that means in size-wise. And reduce the volume of the magnet, reduce total cost, reduce total mass. So if we would have used optimization, we would have achieved all this. Okay, but we did not at that time. Later we did, and later we built another machine, which was much smaller. Okay, and cost us less as well. And efficiency was much better. So this motor efficiency was only 84%. It was only a 1 kilowatt machine, so efficiency 84% was fine. But when we optimize it, you can see the highest efficiency achieved was 95%. So that's why the 11% efficiency increase just through optimization. Okay. So that is all good. So up to here we only consider electromagnetics optimization, right? All the parameters that we check is coming from electromagnetic design. So what could go wrong if we only look at electromagnetics? Okay, what could go wrong? This is an example, let's say for a V-type and flat type case. Okay. V angle is varied, and we are looking at how the torque is changing in optimization, let's say. So for this particular case, we found that okay, V shape gives the highest torque, about 410 Newton meter, and flat type gives us only, I think about 350 Newton meter. So obviously I will use my V type, right? I could have decided that. But if this one is designed for, let's say, a high-speed application, okay, traction motor will go for quite high speed, above 10,000 RPM. So if it is going for application of high speed and I do not check my mechanical stress, then I could choose the V-type. But if I do the mechanical stress of these two design, you see what's happening? Mechanical stress for V-type is about 400, close to 450. Whereas for flat type, it is close to 300 megapascal. Okay? Now the material that is being used, usually the electrical steel, the stress it can withstand is about 300 actually, or up to 350 megapascal. Okay? So if I would not have checked the mechanical stress and use it for a high-speed design, and build a prototype, I could have ended up having an accident. The rotor would have been fly off or broken down mechanically. Okay, so that's why when you do electromagnetic optimization, you should always check, even if it is not high speed, you should always check whether it is within the limit or not. It does not need to be part of your optimization. It could be outside, but you should check. Okay. Similarly, thermal, you must check whether it satisfies the thermal or not. Okay. So that's a normal process. However, in recent time, they are proposing why not include even mechanical thermal during the optimization. Okay, we do electromagnetic optimization, but why not include also thermal and mechanical? Okay, and if we do include it, then it becomes the multiphysics. Okay, multiphysics optimization, and this may be required when you are designing aggressively. Okay, that means you want your machine to operate at the limit of mechanical robustness or limit of thermal conditions. Okay, in that case, you may want to do actually multiphysics optimization. Okay, So that was the case for us when we did this high-speed IPM motor that we have designed. So high-speed IPM design, we are pushing the envelope, right? We are operating at the boundary of the mechanical stress actually of IPM machine. So the mechanical stress must be part of the optimization. And so that's why we had our genetic algorithm-based optimization electromagnetics, but then we added the mechanical stress analysis optimization as well, part of it. Okay. If possible, actually, we should also include thermal, but at that time we did not, because we knew that for high-speed motor we will use force cooling, liquid cooling. So after finding the design, because finding the design itself was very challenging, so we thought we'll find the design and then we'll do the thermal evaluation. Otherwise, like it will take even longer time. Okay, so we developed this, and later we did the thermal analysis. So thermal can be done through some lump circuit model, or ANSYS has a thermal test bands. Thermal test bands can be used as well. So if we do outside, then if the losses goes to the MATLAB, and then use MATLAB can input to the circuit thermal circuit model. Okay? And that gives you the temperature, and then you check whether it is within your temperature limit or not. And another thing is that, as I said, multiphysics means it could take you very long time, okay, because you are doing electromagnetics, which already takes time, and then you are also doing mechanical, or you may do thermal. So you want to actually simplify things or reduce computational time. So in finite, like for electromagnetics component, there is a process called computationally efficient FEM. Okay? So what is computationally efficient FEM does is that instead of, let's say for flux linkage, here it's showing the example of flux linkage, instead of trying to calculate each point of this flux linkage waveform, you simply do 1/6 of the waveform, because there is sinusoidal waveform is kind of symmetrical, right? So if we know 1/6 of the waveform, the rest can be predicted. Okay? So the finite element simply calculates here, let's say, or in this case only these points has been calculated. So that's the computationally efficient FE. And rest of the waveform it will predict, or you can predict, or extrapolate it. Okay, so this is that's how you reduce numeric the computational time. Okay, otherwise, like you may need a supercomputer, or you may need to go for 2 to 3 weeks running your program. Okay, this one I think once we use this, we could reduce it to 1 week. The whole thing still takes time, so you run it for 1 week, and then only you get your results. Something like that. And then similar to this, we also try to, for analyzing mechanical stress, you can use FE, but again, as I said, it takes time, so we could use some analytical model. Okay, so the accurate analytical model was developed, so which was also become part of that mechanical stress analysis part. So partly it was done in the analytically, and then partly done in FE to reduce time. Okay, so you can find our papers on how this mechanical stress model accurate model was developed. You can also read about this paper. We have how the multiphysics optimization was done for the high-speed motor and how it was found. And so a few things was done only for the selected, refined designs, not to the old designs. So one was that in high speed, you also need to check whether there is any resonance in your shaft. So that was done outside. Similarly, thermal was done outside for our case. And the machine that was found is, this is, you can see the rotor. It is, again, it's a new type of design. So we haven't disclosed the rotor design because it is patented. But you can find something in the paper, okay? So the rotor is size, the motor size is just of a ball pen, okay? And it's a 5 kilowatt motor, okay? It's a 5 kilowatt, 100,000 RPM. There's huge interest from actually industry for this motor. That's why we are just being a little bit careful here. So we are not showing you the geometry. We just use neodymium iron boron, and material just we use the highest stress, mechanical stress possible silicon iron material with the highest possible mechanical stress. So no exotic material, it is all easily available material. And you can see the test bed we also developed it because it was it has the fundamental frequency of 3.3 kilohertz. We needed an inverter of 84 kilohertz switching frequency. So that can be done only through silicon carbide inverters. So it is a two-level three-phase inverter, but we use silicon carbide. And so that inverter was part of this test bed itself. So we built two prototypes so that one become load for the other to do the experimental testing. Okay, I think Dr. Vinay Kumar has seen it when he was in our lab. He visited our lab, so he saw it there. Did you see it running? I can't remember. You saw it running, yes. So it was, and the run, because it's high speed, the control, it requires a sensorless control. You cannot have all encoder. Okay, so it used a sensorless field-oriented control. Position was estimated using a sliding mode-based observer. Okay, and it worked fine. It's still working fine. So you can see all these cooling tubes here. So we do force cooling, and it has on the top of the rotor there is this cooling jackets through which the water or cooling liquid flows to keep it cool. Okay. The length of the rotor, you can see it's only 70.7 millimeters, so 7 centimeters. Okay, and smaller than your small scale. Okay. So yeah, so that it was a very interesting project, and once we did it, we saw the huge interest from many different parties for this motor. Because the IPM motor high speed was not possible before. It is a IPMSM. Although SPMSM is there, and high speed SPMSM is there. BLDC is also there, but not IPMSM. So that makes it a bit different from others. And you can see here the comparison of the two prototypes that we have. This is the high-speed, low-torque machine. This is a high-torque, low-speed machine. Okay, so same 4 kilowatt. Both of them are 4 kilowatt machine. So look at the size of the high-torque, low-speed motor compared to a low-torque, high-speed motor. Okay, this first one, this is high-torque, low-speed, is for wind applications, wind generator application, direct drive wind generator application. So it was a 54-pole machine, okay, whereas the other one was a 4-pole machine. Okay, so with high speed, as we talk about, you can reduce size, so that's what it is. But of course, not every application requires 100,000 RPM, so it's will not be suitable for all applications. Right? It is suitable for certain applications. And the finding from this design was that how to make IPM motor robust. Even for traction applications, as we have seen, maximum speed is moving to the higher and higher side, 20,000 RPM. And so whether this design concept can be used even for lower speed, not 100,000, but size will increase as the power level and the speed reduces, but the same robustness can be achieved. Okay. You can also see this how the high speed reduces. So I think this is one of the interesting picture. It is actually from Siemens. Okay, and they have developed this rotor which is 260 kilowatt, so 1/4 of a megawatt. Compare that with this. This is also a 250 kilowatt or 260 kilowatt conventional, I think it was conventional synchronous motor or induction motor. Okay, so this is a load for this motor. Okay, for this motor, and can see the size difference. Okay, and this small size, it has high speed. I think it has 2,500 RPM or something like that. So this motor was developed for aerospace. Okay, how small it is. So in the optimization space, these are the emerging research areas. So if you're looking for research projects, PhD research project, and wondering where to start, so you can see here some of the areas where you can contribute. Axial flux motor for in-wheel application, which is allowing for racing car to eliminate any type of suspension braking, which is seems to be something big for racing car industry. And co-designing the whole system. Okay, co-designing not just the motor but the full system. And torque factory, that's under control. How to torque control if you have more than one motors, or you have 4 motors in the wheel, how to control it effectively. So that's torque factory. And of course, physics design we talk about. Testing methods are still, some of the testing methods not yet developed fully. Hairpin winding, very high voltage in motors, and use of special materials such as nanomaterial, dual phase material, non-rare earth magnet material, etc. Combination of those material with traditional material in the design, so many. Okay, and then of course AI made design as well is there, which probably will come in future. Okay, the use of AI in motor design only has started, so it's a long way to go. So to find probably a lot to contribute there. So this is just showing you how the design, system design, if we want to do system design, how it will work. It's not just multi-physics of the motor, but you have to also consider then your converter design. The converter design becomes part of it. Okay, converter design becomes part of your optimization routine. Okay, and you do it for the whole system level. I think that's the first part. Yeah, tea break. Tea's ready. Yeah, okay, tea ready. So enjoy the tea, and then we'll come back. Okay. Okay, so you can also see how torque changes, speed changes. So to achieve this torque, speed change, we must have proper control, right? If we only have the motor, it's not enough. The motor drive, you must control it sufficiently so that you can have the smooth ride that we experience in the IC-driven car, right? So this part, that's why first we will be looking at the control. We will start with classic P/F control, and then we move to how the concept of flux weakening and constant power is in classic P/F control, and then we will probably move to some more advanced ones, okay? FOC, field-oriented control, or DTC or MPC, etc. So today's talk actually would continue to tomorrow. So let's look at this power and torque equation that we have discussed previously, this is the classic equations, right? And in this classic equation, perhaps most of you know that you can get a constant torque, constant maximum torque in synchronous machine. But if the delta angle is, if the delta angle is 90 degree, we get the maximum torque, right? In a cylindrical or non-salient pole synchronous machine. And speed depends on your frequency. That is like it is always synchronous speed, so speed is your frequency. If I want to change the speed in a synchronous machine, I have to change frequency, right? And that's what you do with your inverter. You're changing your frequency to get different speed. Now if I change frequency, let's look at this classic equation. If I change frequency alone, what is going to happen? If I only change frequency to get different speed, what will happen? Your reactance, synchronous reactance XS is also going to change, right? Or XD. These are all omega time inductance. So if you change frequency, your omega going to change. So this reactance is going to change. And your back EMF is also going to change, right? Because back EMF is omega time flux linkage. So if omega changes or F changes, then this quantity is going to change. So in our torque equation, let's say this is the torque equation here. If I only change frequency to get different speed, this quantity going to change, and this quantity, how am I going to get it? And that, how to get maximum or same maximum torque at any speed actually takes us to the concept of constant P/F, right? So those who have done drive courses, maybe you are familiar with it. So in the same torque equation, we can, let's rewrite it a slightly different way, okay? So back EMF over omega this omega and back EMF, right? So this ratio of these two quantity is actually your flux linkage, right? Because flux linkage time omega is your EA. So ratio of EA over omega is the flux linkage. And in case PMSM, it's a constant value. PMS, the flux linkage of the PM or magnet. So if EA over omega can be, this is a constant. So even if we change omega up, that means EA is going to change proportionally, so it's kind of constant. But if we change omega, we still have problem with the synchronous reactance part, right? So let's expand that synchronous reactance as 2 pi FLS, right? And then this is equal equal to 2 pi f ls. So this frequency part, frequency component, we can then make it as a ratio of V over f. Okay? And keep the 2 pi and ls part out of it. So now if we look at it, it will remain constant even though we are changing frequency, or even though I am rewriting it differently, right? EA over omega is your magnet flux linkage. Okay, this is equal to magnet flux linkage in the RMS value. So lambda PM is your peak value. That's why PM over lambda PM over root 2. And VA over XS, this part, we can also write as VA over 2 pi FLS and VA over F, this ratio. If I maintain PM synchronous machine, also you can do P by F if you want. Okay. So by changing this ratio or keeping this ratio constant, I can get for any speed same maximum torque. But there is some problem, although theoretically it is true, like I can get the same maximum torque for any speed up to 0. But usually that's not the case. If you have done some experiment, you will see that you do not get the same maximum torque at low speed. Very close to 0 speed, you cannot get the same maximum torque. Do you know why? What's the problem with low speed? I'm keeping P by F constant, running the motor, but at close to 0 speed or very close to 0 speed, or let's say 5 to 10% of the rated speed, and I can't get maximum torque if I don't do something. We write it as a lambda PM over dt. What we have written here in this equation is that EA over omega is lambda PM, right? Lambda PM is not changing, correct? Remember? We have ignored resistance. Okay? We have ignored resistance. We said that resistive drop I times R is negligible compared to this type of situation. At close to 0 speed, we will keep this ratio constant, and you can implement, you could have a speed command, so all open loop, okay, there's no closed loop control here. So you have the speed command, and from the speed command you can determine what is your frequency. Okay, because your speed is your synchronous speed. Speed is the frequency since it's synchronous motor. So you know what is your frequency for this particular speed command, and then increase the voltage or decrease the voltage in such a way that this ratio is always maintained. So from this ratio, I can calculate out what the voltage I need for F1 frequency, right? What's the voltage I need if my speed relates to F1 frequency? So I get that voltage, but if for low speed, I will add an extra voltage to my voltage command. So N is that ratio. This ratio we can also rewrite as P naught over P1 F naught over F1. So you can also write like that. So this is how it was written here. And so we get you can construct the reference voltage for your PWM signal, and that becomes your PWM signal will go to your inverter. We also fluctuating. Okay, before I show you the issues, but with P by F control, we can also get fluctuating. So once we have reached the right, if I want to increase speed, so that means what's going to happen now? This frequency is increasing, but at your find that E time I, right? So is my current. So current either could lead your back EMF or lag your back EMF. Synchronous motor is E time, I time, the power, the phase angle between E and I, which is in our case cos gamma. Okay? So this is also the power equation. Okay? This is also the power equation. From get the different torque and different speed based on this equation. If I want to get maximum torque, gamma need to be 0, right? Cos gamma need to be 0. What does cos gamma need to be 0 mean, right? That's why you want ID to be 0. You will need PI, if it is PI controller, the current control is in fact used in the BLDC motor very much. Okay, when the simple BLDC motor, how they do torque and speed control, in fact by this, they simply control current I and gamma with some simple methods. Okay, the proportional, maybe they will do the current proportional to torque, have a lookup table, and try to source inverter may not be able to do it properly. Okay, so for PMSM in traction drive, we cannot actually use this simple method. For P by F control, we cannot do because it is steady state and it cannot handle the transient condition. For make the current coming to the second quadrant, we will get a negative ID, which will be producing a flux opposite to the condition. So if we don't control the transient, this is what you can get, right? We want a smooth drive like this all the time, whether you are accelerating or decelerating. But if we are not controlling properly during this transient condition, if we use a P by F control or the current, then handle the transient response as smoothly as yes. Which one? P by F. Yeah, usually P by F is an open loop control. Sorry. So for this one, or command or not, but you excite all three phases together, right? In this PW, it's not that you excite A phase first, B phase first, or C phase. This control is referred sometimes as I by F control, okay? And the other one is called P by F control. Okay, so I by F or P by F control, right? So you are not controlling them precisely to estimate position accurately. So for those type of application, at the start, they usually use I by F control or P by F control just to start. Bring the speed to a minimum value from where the sensorless control can start. Okay, so even though in PMSM we do not use P by F control for whole thing, but sometimes in sensorless or P by F. But many other applications like the high-speed motor that I talk about, so we use this application. Okay, so you could have the battery here. You may have some kind of a boost converter as well. Controllers that we are talking about, whether it is P by F, I by F, or FOC, anything, so it's here. It is controller, a chip, or a card. Okay, C3000. What you have in your lab? The microprocessor. Sorry. C2000, right? So C2000, in fact, they use something similar in the real world, because in the real world they don't have micro box or displays, right? They have to use some kind of a card like that. Okay, C2000 is the microprocessor So it will be a simple, some like powerful enough, but small enough to be integrated in the inverter itself. Okay, that's how in the real world it happens. Okay, all the controller sits on that microprocessor, and output is the PWM, which will go to your switches. Okay, that's how in the real world it is handled. Nowadays, nobody builds hardware PI controllers. Okay, if you use PI controller, it all sits on the microprocessor only. And then just to remind ourselves, so we could use PWM as sinusoidal PWM, or we could use SVM. Mostly in traction drive, space vector modulation is used, okay, not sinusoidal PWM, because it can utilize more than DC bus. So in SVM, you can use or you can utilize up to 57.7% of the DC bus compared to 50% of the DC bus in the sinusoidal PWM. Okay? Because of that, SVM is preferred for high performing drive applications such as traction. Okay? And so what's the difference? I am sure all of you know PWM as PWM. The SVM, the difference is that you're still going to get these pulses, but these pulses durations are calculated, right? That's what the SVM does, space vector modulation. We have 6 switches. Based on which switch is on, we can get total 8 space vector. We also mentioned what the space vector is, right, last time. So you can get total 8 space vectors. Out of those, when all 3 bottom switches are off, or when all the top switches are off, you get the 2 zero vectors, okay? And others are active vectors because they will have certain values related to VDC. And those 6 active vectors can be plotted in a real and imaginary number plan, which will give you this hexagon. Okay, so each node of this is actually based on the switching states. Okay, so if I want a voltage factor or a space factor at all time, where these and each of these 6 sections is defined as sectors. So your voltage factor required by the space factor required by the motor can sit in any one of these sectors. And let's say it is sitting in the sector number 1, this sector as shown here. To get this voltage factor, one of these 2 space factors must be activated. Okay, so that you can get the resultant vector here, right? Now, in the space vector modulation, you simply try to calculate how long, let's say we call this as 1 and this as 2, how long vector 1 and vector 2 need to be on, okay? So that's, and that way you calculate, okay, the time required for each vector to be on. So here you can see, like for example, let's say this is A phase. To get this pulse, we are let's say up to here. We have 0 vector, vector 1, vector 2, and vector 7 are required, okay, to create this pulse, okay, half of this pulse, let's say. And so V0 need to be turned on for certain time, and V1, V2, and V7 need to be on for some other times. So that the space vector just try to calculate that, okay, for each phases. It's kind of an algorithm, and it's very well-known one, so you just can use what has already been developed there to get your SVM. So either one, PWM or SVM, in each case you need a reference voltage. In case of SVM, this is your reference voltage, right? In case of SPWM, this is your reference voltage. Okay? So either case you will need a reference voltage input to this SVM generation, SVM pulse generation or SPWM pulse generation. Okay, so input is this reference voltage, and this reference voltage must come out from your controller. Okay, so controller's main purpose is to produce this reference voltage basically, and after that it is simply generation of the pulses, right? Let's look at the FOC, general one. We could usually will have a speed controller and two current controllers. So I think you have also went through the hierarchy of the controllers, right? Why the speed controller need to be outer loop and why the current is inner loop, right? So it's a cascade control system. And you may note that now the torque equation we are using here is completely different. Okay, it's not the one we have seen in the previous slides, not the classic torque equation. So where does torque equation come from? Transformation, right? So you have gone through the transformation as well. So what's the advantage of transformation also I think you have learned, right? The DQ transformation or inverse of the DQ transformation is part and parcel of your FOC. And that's why these transformations are matrix, right? If you remember, it's a cos theta sin theta matrix. So for that matrix, we need the information of theta. And that theta comes from your encoder. Okay? And that's why you must have the encoder. Okay? If you are doing FOC with sensor, that means you must have an encoder. If we want to do FOC sensorless, we can do it, but then you have to estimate this theta by some means. We can still do FOC sensorless. Okay? FOC sensorless is possible, but this theta then you must somehow estimate. Okay? Maybe we'll discuss a bit more, like how it works, maybe tomorrow. And then look at the DTC. So DTC again, the main difference between DTC and FOC is that in FOC you have the speed controller and then you have the current. So you are controlling current, not the, even though you want a certain torque. Your main purpose is to get certain torque, right? So you are controlling current, so you are indirectly controlling the torque. Whereas in direct torque control, your command could be a torque. You could have a speed controller here. Output of that speed controller will be torque. Okay? And the other component is flux. So in FOC, we have this torque, but we are controlling this torque via this IQ current. And we also actually have flux control here, but the flux is in this case controlled by ID current. Okay? So we are doing indirect torque and flux control in FOC. Whereas in DTC, your command is a torque, and torque and flux are direct command to your controllers. Okay? And the classic DTC actually does not use SVM or PWM. They use switching tables. Okay? And using the switching tables, they just turn on and off the switches according to that table. Okay, so that table is very important. The whole thing can happen actually in the alpha beta reference frame or stationary reference frame. So you do not need an encoder to do a DTC. Okay? So it is inherently a sensorless scheme, DTC. You do not need encoder. Okay? But then you may ask me, why then we don't use DTC all the time? Right? What's the issue with DTC? The main issue with DTC, the classic DTC, is that because it is switching table based, so you are not producing this vector, the space vector, continuously. You are actually producing these space vectors discretely. So because you are producing them discretely, so that leads to high torque ripple and flux ripple in the system. So you get very high torque ripple, especially, which is troublesome for high performance applications. Okay, high torque ripple means noise, vibration, etc. Right? So that's the issue with classic DTC, and there are solutions which we'll be talking tomorrow maybe. And the last one we will be talking about tomorrow is the model predictive control. Okay, model predictive control is kindly new, or PMSM, kind of new, and it's actually in this type of technique that current is predicted, and using this predicted current, the switching signals are generated based on a cost function. Okay, I think next part of the lecture you will be exposed to what this model predictive control means. Okay. Again, for model predictive control, since we are not using PWM or SVM, it is discrete switching signals going to the inverter. So same problem, large torque ripple and large ripple in the flux. Okay, so that's in the classic model predictive, it's the same problem as DTC. Okay, so we'll be looking at some solutions for these controls tomorrow, and we'll be going more deep into the field-oriented control of PMSM in the next tomorrow's lecture, which will then wrap up this course. Okay, thank you. Yeah, should we stop? Okay, all right. So we'll stop for today. I think the kilowatt per kg, I remember, is about 6. Okay, but kilowatt per liter, I can't remember exactly, but it is pretty high, as you can see the size. So I don't remember the exact figure at the moment. Okay, yes, it is very, very high, dense motor, power dense and torque. Power dense motors, not torque dense, because it's low torque. Okay.
This type of motors are usually employed with the high gears.
So this type of motors, the high-speed motors, are for compressors. Okay, so like large air conditioning systems, and for example in data centers. Okay, or even in the large buildings, shopping centers, etc. You have very high, very large air conditioning system, right? HVAC system. So the compressor that they use, if they can use high-speed motors for as a drive motor, they can reduce size. Okay, the whole HVAC system will be minimized. Size can be minimized. So that's one of the applications. The other application is flywheel. flywheel energy storage, they want high speed so that they can reduce the size as well as can get because in flywheel it is the energy, mechanical energy is stored, right? So it is half J omega square. So higher the speed, the more energy they can store. So they want as well flywheel applications. Other applications like you may be hearing about hydrogen to be used as a fuel. So they're talking about using hydrogen directly in micro turbines to produce electricity. So again, micro turbines uses very high speed machines, generators in that case. And many other applications like drills, mechanical drills uses high speed motors, dentist drill uses high speed motors, and so on. So some applications, some particular applications goes for this type of high speed, with or without gear. They may use gear or they may go for direct.
Second question is regarding, since it is very high speed, the mechanical design would have been very complex.
Yes.
What
So-
are the issues?
So mechanical, that's why the mechanical design become part of the optimization, as I have mentioned. That's why it become multi-physics optimization, right? So for mechanical, because you are riding at a very high speed, so the rotors needs a very high mechanical stress, shear stress, right? And the grease in IPM machine, the grease are very thin, right? The grease on the top of the magnets. So they can easily break. That's the biggest issue for IPM machine not going high speed. And our design, what we did is how to strengthen that iron grease doing certain things. Okay, so that was the invention there. So magnet topology was designed in such a way that it can distribute that mechanical stress and make that thin grease not to break. Okay, you can make the grease wide to make it mechanically robust, but then you will be wasting your magnets because a lot of magnet flux will leak there and then wide grease. That's not a good design, right? So we try to keep it thin but making it mechanically robust by designing the magnet structure in such a way that the mechanical stress is distributed uniformly, not just concentrated on the grease. Okay, that's how actually the problem was solved, the mechanical problem.
Madam, did you employ solid core or laminated?
Laminated. That's the thing. Like solid core, anyone can make it. It was laminated and used conventional, commercially available material. Some people could also use exotic material of very high mechanical stress, but those material may not be easily available, right? So what we did is commercially available material and without sleeve. We did not use any kind of sleeve to make it additional sleeve to make it robust. Just use that iron part as its sleeve for the magnets, but make that iron grease mechanically robust. Okay. All right. Any other question from anybody? No. Okay. Yeah.
Can we apply from GIAN control to PMS directly?
You can, but it doesn't usually perform well. As I said, you can apply. It's not an issue. It will start. It works, but you may get.
But the current run is very high, and the position will not correctly match. The current will run behind.
Yeah, that's why the performance will not be good, right? It even could vibrate. You may get noise, okay, or it may not be operating with the torque it can produce because you are not controlling the torque as a maximum torque per ampere, right? So it is drawing very high current, as you said, because it's trying to produce a torque based on simply the V/F ratios, maximum torque, right? But you have no You are not controlling anything. It's open loop, right?
But the speed also, when I assume the speed will be clockwise, but it will rotate in anti-clockwise because of the position.
It may rotate both directions. I don't think
because of the position it will wrongly rotate in my experiment.
it depends. I mean, in your case it's right, but it may not. It is like we cannot make a general comment that it will always rotate in anti-clockwise. It's not a general comment. Maybe specific to your setup it was doing that. But more, the problem is that it may not be able to produce the torque that it can actually produce, right? If we do V/F. So, like for an experiment, like in our I think undergraduate courses also they do some experiment of V/F control of the PMSM just to understand. So it works, yeah, it does work, but you don't get the best performance out of it.
But you tell that what you design the model will start from V/F, then it goes to
so that is in the sensorless control. So in the sensorless control, usually it's very hard to start them from zero speed without any sensor. Okay, because at zero speed you cannot estimate the position accurately enough, right? Because the position estimation is either based on the back EMF, mostly back EMF, or sometimes it is a saliency, right? But to estimate position at zero speed with saliency, you need to in fact inject high frequency signal. Okay, only with high frequency injection, the position can be detected at zero speed. So you have no option to start the machine from zero speed, right? If you don't have any, if you're not injecting high frequency, there's no option, right? And sometimes even high frequency injection may not be allowed because injection of high frequency can cause again extra loss and extra vibration. So some application you don't have that option. So in that case, how do I start? But I still have a sensorless control. I don't have an encoder. Okay, for my high-speed test bed, I don't have an encoder because the encoder cannot work at that high speed. Okay, we do have an encoder, but it is like very noisy and things, so we just did not use it.
But the differential differences in the signal that will take the noise in encoder.
Whose differential signal?
Differential signal. Nowadays encoder will be like A plus or minus.
Yeah.
It's a noise will be
Yeah. So, but the encoder is kind of a mechanical device, right? So they need to also be robust enough to go to 100,000 RPM. So there's no such encoder. So we could not use the encoder for the high speed. So we bought one. It could work up to I think I don't know 40,000 or 30,000 or something. But it was not good, very good because it is making a lot of noise. So we ultimately decided not to use it. So now we have the problem of how do I start it, because I have no signal and at zero speed high frequency injection can be done, but like if I don't want to do that, then there's no option for me to start the motor. So for that we actually use I/F. Okay, we could do V/F, but we did I/F because I/F is a little bit more accurate, or you have a little bit more control because you are injecting current rather than voltage, so you have the control on your current. So if we don't control the current for magnet motor, it's also risky whether it is going to demagnetization if you push too much current, right? So that's why we did I/F and we are able to start it. And once it sorry? Yeah, so after some time, the sensor will start to give us the accurate position, and then we just move to the sensorless control, OC or whatever control we are doing. Okay, so then we do the sensorless operation. So then during starting, that's why it's I/F is quite good technique to use. It's very simple. It does not need anything, so it's good. But for the full range of operation, it's not recommended. Okay. censored encoder, you have no problem starting. Because if you have encoder and if you are doing FOC, V and F increases in proportion. So if you have zero speed, means your frequency is zero, voltage is zero. Next, let's say you go to 1 RPM. So 1 RPM, whatever the equivalent frequency, and you increase the voltage equivalently, right? So this happens through your FOC itself directly. Okay, so that's why you don't need this damper winding. Neither you need this sort of V by F or I by F for startup. Okay, it will start automatically. Okay, if your FOC is working properly. It's just how good your controller tuning is. If you tune your controller nicely and perfectly, no problem with startup with sensor. Okay?
You said that in position sensor there is a noisy. Can you give me that after this value the noise will effect of noise is very.
After which?
After one speed the position sensor will affect the noise. If 1000 RPM is there,
yeah.
the very noise is too low. So
yeah.
we can eliminate it.
Yeah.
After one point of speed, the noise will become very large.
So it depends on the encoder specification, right? Your encoder data sheet should tell you up to what speed it will give you the best resolution. If it was designed for, let's say, 1000 RPM and you try to use it to 2000 RPM, maybe then its resolution becomes poor, right? And then that could cause problem for your FOC as well, because your FOC completely depends on your encoder theta signal, right? But if it is designed for 2000 RPM, it should not give you noise. Okay, it will have a cutoff filter somewhere in their design itself, so it will eliminate all the noises. That's what we have seen. If then good encoder, they will work. Okay, up to whatever speed they are designed for. Yeah. Okay, and you can always have on top of that, if you, for speed signal, so speed controller, you can have a low pass filter if you want. You can always have a low pass filter. Okay, even outside of your encoder. Low pass filters, but go for some software low pass filter in your control, not a real hardware low pass filter. You don't need to. Okay? There are a lot of nowadays small codes you can write which behaves like a low pass filter, and use those things, that are cheaper and don't need any hardware, and it just becomes part of your control. Okay? Yeah.
Next session will start by 2:50. Okay. The main object of this session is we will try to discuss what is the philosophy behind the direct current control and model fit to control method. We'll see, once you know the philosophy behind the particular logic, we can adopt for multi-level also. We can adopt for different machines also. It will not. See, we'll try to focus on key fundamentals about VPC as well as MPC. Later you can adopt for your system. Okay? Yeah. Next, one more important thing is tomorrow our mandatory is 11:30. 11:30 to 12 o'clock. 12 to 1 exam is there. Before lunch break, we will try to wind up the course. Is it fine?
Yes, sir.
So 11:30 to 11:55 mandatory is there. After the photo session, then immediately exam is there. There is no grading, but we'll evaluate the sheets. Objective and descriptive both are there, right? So whatever content we discussed till now, up to last session, right? Based on our lecture topics will ask questions, objective as well as discount. Phasor diagrams, equivalent circuit diagram, different reference frames, what are the transformation matrix, right? Okay. So, thank you. Session is over. Today no slot, right? 12:30 to 1:15 there is no slot. There is no lecture schedule. Check your session. Difference between V/F, open loop and closed loop. What is the issue with open loop control? What is the advantage of the open? What is the advantage of closed loop control? Anyone?
We do have feedback system so that can monitor the output, whatever output parameters that we are controlling. So the closed loop control, the inverter switching and everything, we can if we put reference, if we put 1500 speed reference, so we have to put the reference to 1500. So the switching operation, the feedback signal will provide the switching operation and that the duty cycle reference.
See, until apply the disturbance on the system, the performance of open loop and closed loop both will give same result. There is no difference between open loop control as well as closed loop control until you apply the disturbance. See, after applying the disturbance, system response will deviate away from the reference in open loop operation. In closed loop operation, even if you apply disturbance, the ability of the closed loop mechanism is it will eliminate the effect of the disturbance so that, see, under steady state condition, actual and reference both are coming in phase to each other. Next, one more important thing is the drawback with open loop control is there is no control on the current. Right? If you want control the current, you need to take precaution even though it is operating in open loop. In industry, how they are adopting, particularly we have Siemens Center in NIT Warangal, right? How they are operating the electrical drives, industrial drives using simple V/F method open loop. Right? They are able to control the current even though it is operating in open loop. Right? See, whenever you want to control the current, what is the basic thing you need to take care? Anyone? Suppose I want to control the current through the motor, what it required? Current should not accelerate, current should not change drastically, or current should not accelerate immediately. Right? Current should be always within the safe zone, within the limit. Right? How we can control the current, whether it is open loop or closed loop? What is the base to control the current? See, if you want to regulate the current, you need to take care about the potential difference between the applied voltage and back EMF. This is a very important point, whether it is a DC machine or AC machine. Right? Whenever you want to control the current, right? Whenever you want to limit the current, first step is you should know what is the strength of the back EMF. Once you know the strength of the back EMF, it is not a big deal to change the input voltage. Let us assume that back EMF is, let us assume initially back EMF is 0. If operating speed is 0, back EMF is 0, you should not apply, as a electrical scholar, you should not apply rated voltage when our operating speed is 0. Initial condition, you should not apply rated voltage, right? How much voltage? Only 10%. Initially, you have to apply 10% voltage and 10% frequency, so that even though your machine is not self-starting machine, PMSM, BLDC or SRM machine, all machines are basically not self-starting machines. Because of VBF concept, we can make it to self-starting machine. It doesn't require any damper winding, special machines. It doesn't require any extra commutator, right? By using logic itself, we can accelerate the machine even operating speed is 0. Example, let us assume that what is the nature of PMSM? Initially NR is 0, there are magnets are there, rotor poles are available initially, right? Initially, see, if you want to generate the twisting force, what is the necessary condition? Relative motion must be 0. You got my point? If relative motion between the stator pole and rotor pole is less, both will interact, right? Then you will get twisting force. Initially, the speed of the rotor poles are 0, then you have to rotate the stator poles with less speed. 5 heads or 10 heads if you operate, then the speed of the stator poles are very, very less. In that case, what will happen at finite condition, your rotor poles will lock with stator poles. Many of the scholars, they are thinking that mine is position control, mine is PMSM, BLDC or SRM machine, right? So without position, how we can accelerate the machine? Position is not required. Position is required whenever you want to improve the dynamic performance. If you are not so interested in the dynamic performance, by using simple VBF method, we can accelerate the machine, but it will take time. It will take long time to reach steady state. Why? Because see, whenever you want to accelerate the machine using open loop operation, necessary condition is current should not go beyond the rated value. To limit the current, what we are doing is practically, right, in industrial application, they will write the code for reference. See, system also one so reluctant. It is not. See here. So initially in open loop, just a minute, I need to. Can I restart? Just a minute. See, what they will do is, even suppose initially your requirement is 1000 RPM, they will not give reference. Even if you give reference 1000 RPM, what will happen? It will apply to the integrator. If you apply to the integrator, what will happen? Your 1000 RPM slowly it will update. So initially only 10% of the reference speed will release. So initially your reference speed become 100. After some time delay, then one more 100 will add to the initial speed. So 200, your reference speed will change from 100 to 200, 200 to 300, like that. It will, your reference speed, it will go in step fashion. Cumulatively it will increase. Even if you give initially 1000 RPM, see, if you write the code, you need to write the code irrespective of your reference, right? Your see, your reference should not go in step way. It has to go in, right, cumulating fashion. So that what is the advantage is we can limit the current. So how we can limit the current? Initially, if you take any drive, operating speed is 0. If reference speed is right, because of control action, because of your logic, if reference speed is coming 100, then back EMF is 0, reference speed is 100, then see, because of impedance, we can control the current, right? So because of initially, 1 minute. Got my point? What is the x-axis? What is the x-axis? Time. Y-axis is reference speed. Right? See? Here, omega m star is the reference. X-axis is time. Right? With respect to customer point of view, even though it is operating in open loop, even if you give reference speed 1000 RPM, with respect to duty period, see, it will not, your duty will not operate with 100%. Your duty will operate only 10% of the rated value. So that only initially 10% voltage will apply, frequency also will apply only 10%. Because of this reason, what will happen? See, what will happen? You will get automatically self-starting. It doesn't require any position control. Your rotor poles are stationary. Stator poles are rotating with less speed, only 10% of the rated speed. Right? So because of relative motion between the stator flux and rotor flux is very less, finite time, both will attract each other. Rotor poles will lock with stator poles. Once rotor poles are locked with stator poles, what will happen? What is the advantage? Current will come back. Right? So this process will take maximum 2 to 3 seconds. That's why you have to provide delay. There is a delay is there, right? Your reference speed become 100 RPM up to 2 to 3 seconds. Later, once rotor poles are locked with, as a scholar, what is the inertia of the drive, you need to understand. Once you know the inertia of the drive, based on the inertia of the drive, we can decide the time period for each stage. If inertia is more, you have to provide freedom. You have to take long period. If inertia is very less, you can reduce the time period. You got my point? What I am trying to say? It is completely depends on the characteristics of the machine, right? Without knowing the inertia, we cannot decide how much time we need to take for each step. Once your speed reaches to 70 to 80% of the base speed, you can reduce the step time. Even if you reduce the step time, current will not increase more than the rated value. Only starting condition below 60 to 70% of the base speed you need to take care, right? But in closed loop operation, we are not adopting this type of mechanism. Your controller logic itself will take care about the B by F method, right? See, actually my pen is not working properly, but it is. I don't know where it is. Pointer is not coming. See, without pointer, very difficult to identify where is my point position, right? See, what is the advantage of closed loop is, see, I am telling, if let us that there is a torque reference is there, right? This is actual torque. If you take PA controller, What is the PA controller? See, PA controller will produce V reference. Based on the current error, your PA controller will produce V reference. How much voltage we need to apply across motor terminal will take care by the PA controller. See, even your reference speed is 1500 RPM. See, to maintain 1500 RPM, required voltage is 100%. 100% voltage you need to apply to meet customer requirement. But thing is, see, to limit the current, what it will do is your controller initially it will produce V reference value only 10% of the rated value. Right? Because of control action, it will take care. Why? Because for each control action we need to take limiter. We have to take limiter, right? By taking limiter, we can control the current. Whenever you want to control the current, only option is voltage. Whatever voltage you are applying, that you need to control. That you need to control proportionally. See, current is controlled through frequency. Am I correct or not? How current is controlled through frequency? Frequency, by changing frequency, we can change the speed of the magnetizing poles. The speed of the magnetizing poles and speed of the rotor both are very far, then relative motion is more, you will not get twisting force. Back EMF is 0. There is no twisting force, there is no mechanical energy, back EMF is 0. Machine will take huge amount of the current. To see, that's why your controller, what it will do is, if it is open loop, you have to write the program to get step voltages. But in closed loop, your logic will take care, your logic itself will produce this type of voltage, irrespective of the reference speed. Please understand. Whatever reference speed you are giving, right, it will not bother you. Simply, even if you give 500, immediately 500 signal will not, what is the corresponding voltage, right? To meet 500 RPM, same voltage will not apply across motor terminal. It will apply only 10% of the rated voltage to limit the current. Right? This is about current control concept for all electrical system. Whenever you want to control the current in open loop, you have to see what is the main cause component. The main cause component to accelerate the current is potential difference between the voltage and back EMF. These two difference between the back EMF and voltage you need to take care. Speed is 0, applied voltage must be 10% of the rated value. Like that you have to write the code, you have to write the program. Right? Once speed is accelerating, then further you have to increase the voltage. Once back EMF is coming closer to voltage, further you can increase the voltage again 20%, 30%. You have to give freedom to the rotor. So once rotor is coming in phase with your requirement, then step by step you can accelerate. This is what they are doing in the laboratory Siemens drives application, right? In open loop, most of the drives in Siemens they are operating with open loop only few drives. Whenever high dynamic performance is required, they are operating with closed loop mechanism, right? And anyone having doubt about previous sessions? Why? Because I don't have any chance. This is last session for me. Any doubts are there, you can ask. Then otherwise I will start actual topic of today's session.
Sir, for current controller, if it gets saturated.
Current controller it will not get saturated. Why it is saturated? Your controller, like that you have to design the Kp and K values. To avoid the saturation, you need to design the controller, right? So that what will happen, your current always operating below the saturation. Current will not enter. Based on your Kp and K values, can I explain one example? See, in control engineering, what is the function of P, what is the function of I, what is the function of D? Why combination? We should not take individually. P, I and D we should not take. We need to take combination. P, I and D. What is the function of P? What is the advantage of P? What is the limitation with P? Proportional. What is the advantage? That is the drawback. Error we cannot control through P controller, proportional controller, but we can improve the dynamic performance. Transient performance we can improve. What is the What is the advantage of integrator? By using integrator, we can eliminate the error. But problem is, what is the issue with integrator? What is integrator? Mathematically, 1 by s. Mathematical integrator is 1 by s, nothing but we are introducing pole at origin. If there is any pole is closer to origin, bandwidth of the system will come down. But because of integrator, what is happening? Bandwidth of the system, it is completely become 0. We are introducing pole at origin. Because of this reason, dynamic response, it will become very poor. Steady state response is very good, but dynamic response is very poor. Clear? Now, see, that's why practically they will take combination. By taking the combination of P, I and D, we can satisfy the customer. Take bottle, water bottle. See, take water bottle and glass. If you want fill the glass with water bottle, what we are doing initially, suppose there is a glass is there. My requirement is I want to fill the glass without overflow the water. Right? Initially, if glass is empty, then we have to keep position like this. This is nothing but P controller. Right? Once water reaches to 60 to 70% of the rated position, then you have to change the position. You have to change the bottle position. Right? This is I. Next. Once your level is reaching to 90 to 95% of the actual value, then you need to change the bottle position like this, so that we can this one control the drop. Initially, water is flowing like flow. Later, drop it will go, right? So, last stage is derivative. By using derivative, we can control the overshoots. Right? By using integrator, we can control the error. By using proportional controller, we can control the transient time. Without this position, what will happen? It will take long time. Am I correct or not? Proportional controller, see, the main drawback is we cannot eliminate error. Now, question is, what is the significance of integrator? How integrator will eliminate the steady state error? Otherwise, let us assume that error is 0. How it will produce the control signal? Your integrator. These all are fundamentals. Take KP. K. Add this to. Right? Here error. Let us know there is a current error is there. Let us know that current error is 0. If current error is 0, what is the output of Kp? It is 0. But K error, K output, it is not a 0. It is a finite. That is called modulating waveform. You got my point? Now question is, why even current error is 0, why Ki is always finite? Ki output is always finite. What is the reason?
Cumulative.
It will store the previous data, previous instant, right? Based on the previous instant and current instant, it will add the data, add together, and it will produce the required modulating signal to make error 0, right? But PI controller, it is based on the current instant. I integrator will work based on the current and past instant. Adding derivative, current and previous state difference. It will take difference. Cumulative it will add, right? So this all are the fundamentals. Say whenever you want to control the current, particularly in electric drive system, right? If it is an open loop system, you have to write predefined program. Right? How much time we need to apply 10% of the voltage, how much time we need to apply 20% of the voltage, you have to write predefined program so that we can control the current. We can able to control the current even though it is open loop system. Right? Right? So after that, see if it is a closed loop mechanism, you need to take saturation block. By taking saturation block, we can limit the current. So to limit the current, how much voltage and frequency is required, your controller will take care. We don't need to worry. Right? See, if you refer any textbook, they will not mention about this point. The nature of the voltage applied across the motor terminal, right, irrespective of the reference speed is always, this is the nature of voltage. This is the nature of voltage and frequency applied for all AC drives in any system irrespective of your reference speed. If reference speed is 1500 RPM, don't think 100% voltage and 100% frequency will apply across motor terminal initially. Initially, applied voltage, even reference speed is 1500, rated speed, also applied voltage across the motor terminal is only 10 to 12%. Frequency also 10 to 12%. Because of this reason, we can able to control the current. To limit the current, your controller will take care about how much frequency is required, right? What is the speed of the magnetizing force based on the rotor speed, right? It will calculate. If relative motion is more, what will happen? Relative motion is more current will take. Machine will take more current. That is the issue, right? Once rotor poles are locked with stator poles, current will come down. Then again your controller will accelerate the voltage and frequency. This is the standard principle for all electrical drives if it is operating in closed loop, right? In today's session, we will try to focus on direct torque control. See, even if you take FOC, direct torque control method or feedback linearization, any method, inherently we are adopting V/F method. Don't think V/F is nothing but open loop. Don't think V/F is nothing but closed loop. For all electrical machines, right? Inherently, all methods, whatever methods they have proposed in integration, all are operating with V/F only. Without V/F, we cannot maintain, we cannot minimize the number of variables involved in the torque expression. Without V/F method, we cannot produce maximum torque, even operating speed is less. You got my point? See, V/F is common for all methods, whether it is a scalar control or vector control method. V/F is common. Now, see, thing is, what is the limitation of field orientation method? Yesterday we discussed, right? What is the main limitation of the field orientation? See, challenging is field orientation is estimating the rotor position is so important. If rotor position estimation is not clear or not correct, then what will happen? Whatever, right? Whatever, see, what is the object of field orientation? We need, see, to minimize the order of the torque expression or to improve the torque profile of AC machine from 7th order to 1st order, we are adopting field orientation method. But thing is, if position is not estimated, rotor flux position is not estimated accurately, more accurately, then your algorithm will not work fine. Then torque response will not improve same as DC machine. Why? Because transformations are there, calculations are there, too many calculations, indirect field orientation. There are a lot of calculations are required to get rotor flux position, right? So next, one more important thing is rotor flux position estimation method. If you observe, right, there are a lot of parameters also involved in the system. Whatever parameters we are adopting to derive the rotor flux position, that parameters practically it will change. Inductance will change. If button on the motor shaft is increases, definitely inductance will get effect. Inductance become decreases. Inductor will come down because of saturation effect. At the same time, resistance also will change because of heating effect. So whatever parameters we are taking, right, with that parameters, it will not give sufficient delta calculation. Rotor flux position calculation, it will not that much accurate. That's why, right? So if your system is operating more time, field orientation method will not work effectively. So heating effect is very less. If operation period is very less, you can go for field orientation. But if you see, requirement is with respect to drive point of view, if you want to operate more period because of heating effect, right? More period, more load is there, definitely parameters will get affected. But advantage of the DTC is it doesn't require rotor flux position, right? Next, at the same time, in case of DTC, flux position is required, not that much accurate. Right? Even there is any error is there, fine, it is fine. Right? Now, question is, what is the logic behind director? How many participants know about the DTC? If you know very well, I don't want to put more concentration on this one. I will try to put more concentration on model predictive control method. How many of you know about the principle behind the director control? Can you raise your hand? 1, 2, 3, 4, then 5. Okay, 6. I will explain logic behind this. Okay, I will not go in detail. Right? So here, if you observe this equation, this is called universal torque expression. Universal voltage expression. Yesterday we discussed, if you want to develop mathematical model, what is the universal voltage expression? Applied voltage equal to resistance drop plus d lambda by dt. Right? Next, one more important thing is in DTC or FOC, what we are doing is we are trying to control the resultant. Right? In FOC, what we have done yesterday, we tried to control the resultant magnetizing flux as well as resultant torque producing component. ID is nothing but ID main ID responsibility is to control the resultant current, resultant torque producing current. It will control. The main object of ID is it will control the resultant flux. Right? We are concentrating on resultant, on net. Here also in DTC, if you take resultant voltage and resultant flux and resultant current drawn by the machine, this is the mathematical expression for resultant flux and resultant voltage, right? Resultant current. What is the nature of resultant flux? It is rotating. Resultant voltage, rotating. Resultant current, all are vectors, all are rotating in nature. Right? So by taking this equation, we can understand the logic behind the director control. Right? So this is the universal voltage expression common to all electrical machine. Even if you take PMSMFTE machine, synchronous, conventional synchronous machine or induction motor, right? Even if you take IPMSM machine, synchronous reluctance motor, right? BLDC also, this equation is applicable for all electrical machines, right? So from this expression, if you write in terms of otherwise this equation without losing any property, delta is equal to, right, Vs into delta T. What is Vs and what is delta T? What is delta T? Delta T is nothing but time instant sample. So it is a fix. It is not a variable. Whenever you want to change the flux, it required voltage. How much voltage, how much resultant voltage you are applying in particular sample period is so important to regulate the flux. Please try to understand. This is not resultant flux. This is change in the flux. You got my point? So this is the mathematical model for change in the flux. Delta is is nothing but change in the flux in particular sample. Right? So in particular sample, by choosing proper Vs, we can able to control change in the flux. We can accelerate or we can deaccelerate the flux. We can increase or decrease the flux based on selection of Vs. Right? Next, see. So by using this equation, we can conclude that even if you take DTC, our target variables are torque and flux. Our main objectives are torque and flux. These two are control objectives to meet our required speed. If you want to satisfy customer as a controller, you have to target these two variables. Right? Next, while controlling the torque, you need to take care about magnetizing flux. Magnetizing flux throughout the operation, you need to maintain constant. If you want to maintain constant, only option in AC drives is V by F you have to adopt. Inherently there is a V by F is there in DTC also. Right? Next, by using this equation, we can conclude that flux we can control by choosing proper voltage in a particular instant. Right? Next, come to torque expression. This is the universal torque expression which is applicable for all reaction torque machines. Induction machine, it is useful. Even PMSM machine also this is useful. But surface interior PMSM, what will happen? Reluctance torque will enter in the picture. Yesterday I think I asked one question. What is the difference between reluctance torque and reaction torque? What is the advantage with the reluctance torque? Anyone? What is the drawback with reaction torque? What is the advantage of salient pole synchronous machine? See, salient pole synchronous machine generally to improve the voltage profile, right? Under no load condition, they will connect the salient pole synchronous machine at the grid, right? So whenever they want to improve the voltage profile, what they will do is they will excite the rotor poles beyond the rated value, over excitation. You got my point? By exciting this synchronous machine under no load condition more than the rated value, the ability of the synchronous machine is it will produce the reactive power, so that voltage will balance, voltage profile will improve, grid voltage profile will improve. That is what we have studied in power system or electrical machine also, right? You got my point, right? Now tell me here. Question is, what is the advantage? What is the advantage of reluctance torque? If you verify the mathematical model for reluctance torque, it is always independent of the excitation. If you want, you can check. It doesn't function of the magnetizing flux. It is only function of how much voltage you are applying. Based on that one, it will decide, and also based on the reluctance of the machine, what is the reluctance ratio? Based on that reluctance ratio, it will change. But reaction torque problem is if there is any problem with strength of the magnetic poles, if permanent magnet pole strength, because of heating effect, it may lose their strength. Once permanent magnet strength is losing, if it is a surface PMSM machine, what will happen? There is no torque generated by the machine. The strength of the torque generated by the machine will coming down. But reluctance torque is always independent of the strength of the magnetizing poles, right? Even excitation is failure, salient pole synchronous machine, whatever salient pole synchronous machines are connected to the grid, it will continuously operating in motoring mode only. With reluctance torque, your rotor will drive continuously. Even see, once field current is failures, reaction torque becomes zero. But reluctance torque never becomes zero, even field current is zero for conventional synchronous machine, right? See, for each and every system, advantages are there, drawbacks are there, right? Now, by taking this equation, we can understand, right, how we can control the torque. Next, one more important thing is practically whatever machines, if you purchase standard machines, how they will design the standard machines? Standard machines generally they are dedicated for industrial application, not for domestic application, and not for improve the high performance. Industry, see, high performance, see, standard machines they will develop based on the industry requirement. With respect to industry point, right? Electric motors, they will select the electric motor based on their predefined specification. What they are expecting, industry, whatever machine they are purchasing, first they will verify what is the time constant of the stator winding, what is the time constant of the rotor winding. They will take care. They will through experiments we can get what is the time constant of the rotor circuit, what is the time constant of the stator circuit we can get. If rotor time constant is less compared to stator time constant, advantages controllability will improve. You got my point? Rotor dynamics are poor compared to stator dynamics. If stator dynamics are very good compared to rotor dynamics, ability of the controller will increases. We can effectively control. So because of this reason, what we are using is particularly in direct torque control, we are assume that dynamics of the rotor flux is poor compared to stator flux. Stator dynamics are very good, very fast, but rotor dynamics are very poor. Based on these assumptions, if you refer any standard papers, they will explain simply like that. Am I correct or not? Right? So dynamics of the rotor flux is very poor. Let us assume that this is the GIAN, this is about GIS. Practically, if you take induction motor, if it is operating in motoring mode, the nature of rotor flux always lags the stator flux. Speed of the stator flux and speed of the rotor flux both are operating at synchronous speed. Both flux vector speed is same, but right, if you verify the position of the rotor flux, it is always lags the stator flux with load angle. That is called load angle delta. Clear? How we are going to control the delta? Based on that one, we can decide the performance of the torque profile. Torque profile is completely depends on how you are regulating the delta, is so important. Clear? Now question is how we can control the torque by using this equation. How we can control? How we can control the torque? See here angle is there, delta is there, right? By adding or subtracting delta, we can control the torque. By increasing the space displacement angle between the stator to rotor flux, or by decreasing the angle between stator to rotor angle, we can control the resultant torque produced by the machine. Right? So finally, in DTC, we are concentrating on change in the flux as well as change in the torque. These two, our aim is change in the flux, not total. So if in each instant, if you're taking care about the how much change in flux is required, how much change in the torque is required, if you are as a controller, if you satisfy this requirement, right, over the period, if you take waveform, it will come to in phase to your requirement. You got my point? Instant to instant, if you're taking care about these values, if you take average value over the period, the average value will always come in phase with your reference. That is the beauty of this DTC, direct torque control method. It is an instantaneous base control. It is a instantaneous. Space vector PWM morning, Professor Rukmini Datta, she was explaining. I think one or two they asked doubt, right? What is doubt they ask mornings regarding space vector? Actually, I also forgot. Anyone remember regarding space vector? Anyone? Okay, leave it. Later, so what is my request is, if anyone having doubt, you can send mail, right? So that we'll address. So this is about resultant phasor diagram about the stator flux and rotor flux, right? This is the actual flux position. This is the rotor flux position. What is the assumption? What we are assuming here? What is the assumption? See, whatever position is there for rotor flux vector at t equal to kth instant, right? Even if you take t equal to k plus 1 instant also, after next instant also, the dynamics of the rotor flux is very poor. It is not changing. Nothing but ZR of k plus 1, both are same. Position is same. It will not change. Why? Because our assumption, see, like that they will design the machine. Instant to instant it will not regulate. Suppose at instant 1 angle of the ZR is 45 degrees. In next instant also angle of ZR is 45 degrees only. It will not change immediately. Why? Because like that they will design the, they will take care about the L by R ratio of the machine winding. They will regulate the X by R ratio of the stator coil as well as rotor coil so that we can achieve this condition. In domestic application, you no need to bother about X by R ratio of the stator winding, X by R ratio of the rotor winding. But in industry people, they are very much serious about this X by R ratio about the stator winding. What is the X by R ratio? What is the X by R ratio of the rotor? They will take care. If time constant of the stator is very good compared to rotor winding, then control ability will increases. If you want to increase the ability of the controller, time constant of the stator winding should be very, very less compared to rotor winding. Rotor dynamics intentionally they will make lazy. If rotor dynamics are very lazy, what is the advantage? We can control the position. We can able to control the delta. We can see rotor dynamics are lazy. Advantage is only with respect to torque profile it is advantage. There is no advantage with respect to flux control. Please try to understand. By taking care about X ratio, we can satisfy only torque variable. Right? X by ratio, it is no more related to magnetizing flux. Right? So from this equation at t equal to kth instant, this is the position of stator flux, this is the position of rotor flux. Now requirement is, if you want to accelerate the torque and if you want to increase the strength of the stator flux, right? Let them that see actual flux and delta, right? Delta xis, if you add to the actual flux vector, delta xis is nothing but, what is delta xis? How much voltage we are applying in particular sample is nothing but delta xis, right? By selecting the proper voltage vector, then we can this is about after t equal to k plus 1 instant, this is the position of stator flux. At t equal to k plus 1 instant, where is the position of rotor flux? Here. This is about delta plus delta. Your rotor angle is increases. At the same time, stator flux length is also increases. See, thing is here important, the beauty of DTC is by selecting the proper voltage vector, we can control the torque and flux at the same instant. Same switching time period, same sample time, we can control torque and flux. Right? Clear? That is the strength of DTC. The full form of DTC is direct torque and direct flux control. Simply our main primary objective is torque, that's why it is called direct torque control. But what we are control is flux also we are controlling, direct torque and direct flux control method. See here issue is, this is about block diagram of the control, diagram of the direct torque control method. See, hierarchy of the control logic is same for any electric drive. See, if you take reference speed as a reference, then compare with actual speed, then speed error you have to send through the controller. So controller will produce reference torque. Torque is the main cause component to regulate the speed error. Again reference torque you need to compare with actual torque, then what you will get? You will get torque error. Similarly, there is one more path is there for flux controller, right? The object of this path is torque controller. This is for torque controller, this is for flux controller. See, the beauty of hysteresis flux is, once you take hysteresis controller, implementation is easy. It is not a big deal. But if you take PA controller, implementation is very difficult. Next, compared to hysteresis controller, PA controllers are little bit lazy. You got my point? Integrator, because of integrator, your control signal will not change instant to instant. Next, one more issue. I want to tell one important topic. You heard about anti-wind-up controller. How many participants know about anti-wind-up controller? You heard at least name anti-wind-up controller. No, it is. It will reduce. I will see what is happening is without saturation we cannot control the current. See, once you adopt saturation, once you take integrator, the combination of saturation and integrator will create issues in the practical condition. See, actually, if there is any break is there, what we are doing in general, after completion of 11 to 12, what we are roaming outside, right? We are going out of the boundary, right? So if student is very lazy, he will go little bit far. If student is too lazy, he will go out of the institute, right? By adopting the anti-wind up, what it will do is, anti-wind up is like security guard. He will not allow the students to go out of the boundary, right? He will bring he will always bring near to the boundary. He will not allow the students above the seminar hall complex, right? So it is a very beautiful concept, anti-wind-up controller, right? So here one more important thing is, if you take hysteresis controller, advantage is you no need to bother about uh, you no need to introduce eye controller. You no need to bother about delay in the response. By adopting hysteresis controller, we can your hysteresis controller will respond for each instant, but integrator will not respond for each instant. You got my point? So your hysteresis controller at any instant of the time, it will produce, at every sample period it will produce the state 1, 0, -1. Now here question is, for hysteresis controller, why we need to take 3 states? For flux hysteresis controller, why we need to take 2 states? What is the reason? Why we need to take 2 states for flux controller? Why we need to take 3 states for torque controller? First try to understand question. At the same time, what is our main object also you need to keep in your mind, so that you will get clarity about the priority. For torque controller, there are 3 states. 1, 0, -1, a positive error. If error is from, once error is exceeding on the positive side, you will get +1. If error is between, right, see 0 to 1, it will treat it as a 0. 0 or below -1, it will treat it as a 0 only. Once error is exceeding the +1 or error is exceeding the -1, then only hysteresis controller output become +1 or -1. Remaining condition, it will produce 0 state only. You got my point? See, one more important thing is, whenever you want to decide the bandwidth of the hysteresis controller, you should not select bandwidth of the hysteresis controller simply like that. You should know what is the rated torque of the machine. Once you know the rated torque of the machine, right, let on that rated torque of the machine is 10 Newton meter. Hysteresis controller bandwidth, we can take 10%. 10 Newton meter, 10%, how much? 1. So upper limit we can keep 1 Newton meter, bottom limit we can keep 1 Newton meter. Whenever torque error is more than 1 Newton meter, immediately your hysteresis controller will produce +1. Right? Next, if torque error is less than 1 Newton meter, see error is more than -1 Newton meter, immediately it will produce -1. Now question is, why we need to take 3 states for torque? Why not for flux? Same 3 states we can add to the flux controller also, right? 0, -1, 0. It is under your control. These states are under your control. You can modify. Negative. No, see, negative -1 is nothing but decreasing. +1 is nothing but we need to accelerate the torque. -1 is nothing but we need to deaccelerate the torque. Right? Next, 0, nothing but no need to change the state of the torque. That is the meaning. Now my question is, why we are not taking these 3 states for flux also? Why we are taking only 2 states for flux hysteresis controller? You got my point? These states we can change. It is in your hand. Yeah. It will improve. If you take more states on the torque profile will improve. Our top priority in electric drive is, our primary object is torque control. By taking more levels, right, if you are able to concentrate on torque profile effectively, what will happen? Performance of the torque will improve. right? So further, if you take flux control, our secondary object to control variable is flux. Instead of taking 2 states, if you take 3 states, what will happen with respect to voltage switching state? Complexity will increases. Switching state selection become more complicated. If number of switching states are more, switching state table become more complicated. That's why, see, they are giving top priority for torque controller, right? So that's why they have taken 3 states for torque controller, 2 states for flux controller. Next, one more important thing is, right? Even if you take 0, what is meant by 0 state? 0 nothing but your flux will not get affect, torque also will not get affect. But if you apply 0 continuously, your average value will get affect. See, because of 0, instantaneous value will not get affect. If you apply 0 more instants, your average value will get affect. You got my point? That's why you should not apply 0 continuously. Based on the requirement, based on the situation, right? Your controller will take care. Your controller will take care of everything. Thing is, right, if you want to improve the performance, the bandwidth of the hysteresis controller should be 10% of the rated torque. Next, flux hysteresis band, you need to take 2 to 3% of the rated flux. If rated flux is 1 Weber, you need to take hysteresis band of the flux controller is, you need to take 0.1 to 0.2 Weber. So that we can control the switching frequency. Switching frequency also will not go beyond the particular value, right? If you're taking care about the bandwidth of the hysteresis bandwidth levels, see, hysteresis levels, if you're taking care, we can control the switching frequency. One more important thing is, in case of DTC, we cannot access switching frequency directly. Switching frequency is not under your control, but maximum switching frequency we can limit through by selecting the range of the switching states or range of the width. You got my point? Directly we cannot access, but we can take care about the switching frequency by increasing the bandwidth. But problem is, if you increase the bandwidth more, performance will degrade, right? So next, one more important thing is this switching DTC they have proposed in 1980s. So in 1970s, FOC they have proposed. Next, the logic behind the DTC is, first, based on the operating characteristics of the actual system and inverter characteristics, by adding these two together, right, switching states of the inverter and actual system characteristics, we can improve the performance. We can improve the performance of the electric drive, right? Whenever you want to control the flux, or whenever you want to change the state of the torque, essential thing is you should know where is the actual flux position, right? What is the length of the flux? You should know what is the torque generated by the machine. If you know, we can easily identify. Based on the hysteresis states, we can identify whether we need to accelerate the torque, or we need to deaccelerate the torque, or we need to accelerate the flux, or we need to deaccelerate the flux in next coming instant, will decided by your hysteresis states. Based on the hysteresis state, you have to write the lookup table, predefined lookup table, right? This, see, in predefined, whenever you want to develop lookup table, right? This is what they are doing. This is about, right, selection of voltage vector based on the, see here, this is the actual flux position. This is the stator flux position at kth instant. This is the rotor flux position at kth instant, right? What is the requirement? What is the condition? What is the condition? What is the requirement with respect to control point of view? Requirement is torque state is positive 1. Torque is positive, flux is also positive. Positive nothing but you need to accelerate. Requirement is you have to accelerate the torque and flux, right? If you want to increase the flux and torque, see, particularly your job is you need to identify where the location of the actual flux. You no need to know where is the position of rotor flux. If you know the, see, I am telling, estimating the rotor flux is very complicated. Estimation of stator flux is very simple. How we can estimate stator flux? Simple. If you know the DC link voltage, we can easily estimate the stator flux position. Right? By using DC link voltage and switching states, we can calculate what is the resultant voltage applied across the motor terminal. Right? Resultant net voltage we can calculate. By using current sensor, we can calculate ISRS drop. Right? So resultant voltage minus ISRS drop, you have to calculate, then apply integrator, you will get resultant flux, net flux, magnitude and position you will get. Right? Now let us assume that our stator flux is in sector 1. Now question is, why we are starting sector number from here? But if you take inverter switching states, this is about inverter switching states. Where is the position of V1? This is the position of V1. Right? This is the position of V2. Our vector V1 is in phase with x-axis. But in DTC, why we are not taking sector number from 0 degrees? Any reason? You got my point? What is my question? We are not calculating the sector number from 0 degrees onward. 0 to, see, total locus in DTC, what they are doing is they are splitting into 6 parts. 60 degrees. Each sector number is 60 degrees. But if you verify the sector position, sector 1 position, this is about sector 1 position. This is the area of the sector 1. Your sector 1 is starting from, this is 330 degrees. This is 30 degrees. Am I correct or not? So total area is 60 degrees. Total angle is 60 degrees. Why we are not taking sector with respect to 0 degrees? Why we are starting the sector at theta equal to 330 degrees? Any reason? No. Here I'm not. Just a minute. I will show. See, your flux is rotating. This is the nature of magnetizing flux. It is always rotating with synchronous speed, right? So here what we are doing is this total locus we are splitting into 6 parts. That is up to you, right? So here what we are doing is we are starting here. We are taking this zone as a sector 1, this zone as a sector 2, this zone sector 3. This one, deciding the sector number, angle, everything is under your control. You got my point? This is all our calculation. We can define. There is a circle is there. This zone is sector 1. That is up to you. We can define the location. Name we can define based on our requirement. Now my question is very simple, right? Same circle, we can define like this also. This is sector 1. Sector 2 also we can define same as space vector PWM, right? Clear? 3, 4, 5, 6. Why we are not defining like this? Any reason? Huh? Yeah, even if you take top one or bottom one, we have to select. See, based on the position, you have to select proper voltage vector to regulate the torque and flux. Now, my question is why sector number 1 is not starting from 0 degrees? Why it is starting from minus 30 or 330 degrees? Why it is starting from here? At least one student, many students, they have raised, they are working on DTC. Tell me, what is the reason? There is a reason is that if you start from 0 degrees, what will happen? The nature of resultant flux, it is not a sine triangle or this is not a space vector PWM. It is a hysteresis controller. You got my point? If you start from 0 degrees, the nature of flux, it will go like this. It will go like this. If you start from 30 degrees, 330 degrees, your flux will rotate in this cycle. Which one is advantage? This one or this one? this is hexagon, right? This is unwanted. If you start from 0 degrees, if you want, it is only program, right? You can verify in simulation, take sector 1 from 0 to 60 degrees, right? Sector 2, 60 to 120 you can take and execute your logic. Then you will get, this is the, you will get this type of flux. Otherwise, if you take from 30 degrees, 330 degrees, right, and execute, then you can notice what is the nature of flux. If you start from 330 degrees, this is the nature of resultant flux. Area flux will rotate in pure circle shape. But if you start from your control logic with respect to control point of view, if you take a reference axis for sector calculation from 0 degrees, you will get this type of waveform. This type of waveform. This is the issue with hysteresis control. This type of flux will produce because of hysteresis controller and sector calculation. If it is a signed PWM or space vector, it is not an issue. But with combination of switching table and hysteresis controller, sector calculation, while calculating sector, you need to take from minus 30 degrees. Nothing but 330 degrees you have to start. So that what will happen, resultant flux become sinusoidal. Otherwise, it will go in hexagonal. That is the issue with selection of sector number is also crucial in DTC, right? So how many points are very crucial in DTC? First thing is, first you need to take care about actual system behavior. Actual system, with respect to actual system behavior, stator time constant should be good compared to rotor time constant. This is the essential. While purchasing the machine, you need to take care about what is the XPR ratio of the stator winding and XPR ratio of the rotor winding. You need to take care. After that, with respect to control point of view, you need to take care about the how many levels you have to decide for torque controller, how many levels you have to decide for flux controller. You have to take care, right? After that, selection of switching table is mainly based on flux position, right? That flux, where is flux? While deciding the flux position, you have to predefine the sector number. So while defining the sector number, where the reference point is so important. If you take reference point from 330 degrees, advantage is net flux becomes circle. Otherwise, it will go in hexagon fashion, right? If time is there, sufficient time is there, I will show through the simulation so that you will get more clarity, right? So these are all the various examples. So in sector 1, next one more important thing is, what about this one? What about these vectors? Inverter switching states. See, actually inverter switching states are fixed. We cannot do anything about the power electronics side, right? Once you select V1, the resultant vector will come in phase with x-axis. If you select V2, net voltage will come here. If you select V3, so once, these are all the fixed state. Inverter switching states won't alter. It is a fixed, right? See, based on the requirement, based on the situation, by selecting the available voltage vectors, we can able to control flux as well as torque. Don't think total flux we are controlling total torque. We are controlling only change in a particular sample. So if you are taking care about the each sample about the torque and flux, so over the period, if you verify response, resultant response, it will come in phase with your reference. That is the beauty of director control method. See, so finally this is about optimal switching table, switching sequence for the director control method. So if you take the switching table, this is called heart of the controller, right? Clear? Suppose you want to adopt multi-level. See here in this case, we define the switching table based on the power semiconductor element. We have taken 2 levels, 3-phase 2-level voltage source inverter. If you take 2-level 3-phase voltage source inverter, how many switching states are possible? Maximum 6 active vectors and 2 null vectors are possible. Beyond that, we cannot do anything. So based on the available switching states, you have to define the logic. So if you want to develop this logic, how many inputs are required? Check how many inputs are required. It required 3 inputs. One is flux state is required, flux information, what is the what about the seriousness of the flux error? What about the seriousness of the torque error? You should know. At the same time, where is the position of actual flux position is also important. If you know sector number, and if you know the seriousness of the torque error, and if you know seriousness of the flux error, this hysteresis controller will give the information about what is the seriousness of the error. You got my point? Positive one is nothing but actual signal is less than your reference. Error is positive. You need to accelerate. Right? Hysteresis state is -1, nothing but error is negative. So error is negative, it is more serious. It is crossing your bandwidth. That is the problem, right? That's why hysteresis states will give seriousness about the error based on the seriousness about the error, right? Based on the seriousness of the error, we have to select proper switching states so that we can control the torque and flux in particular sample period. Clear? So this is about simulation block diagram of the direct torque control method. Reference speed, right? This is speed PA controller, right? This is about torque controller. Torque, it required 3 states, right? It is simple relay, right? Relay block. By taking relay, we can identify the seriousness about the error. If error is crossing the limit or not, we can define, right? So this is about flux. So finally here, this is for flux controller, this is for torque control, torque state, flux state, and sector number. By using this one, by using these 3 inputs, we can able to generate the what is the state of the SA, SB, SC we can define. SA, SB, SC are the A phase switching state, B phase and C phase switching states. These 3 switching states you have to apply to the inverter so that, right, what will happen, voltage and frequency will regulate according to the duty period of the SA, SB, SC. Then what will happen here, variable voltage and variable frequency will apply to the induction motor, then torque speed characteristics will regulate based on the requirement, right? So this is about parameter defined in the hysteresis controller relay, right? This is about flux controller parameter defined. So rated flux is 1 Weber. You need to take width of the hysteresis controller. For flux you can take 2 to 3%. 2% is 0.02 Webers. 0.02 minus 0.02 you can take, and you can define what are the outputs. If error is greater than 0.02, then expected output will come 1. If error is less than 0.02, then expected output of the controller is -1. Like that you have to define the switching states. So this is the logic. This is the logic about, see, if you observe this logic, this is about calculation of the sector number. Next, one more important thing is our angles are always in terms of radians. Don't think angle is in degrees. Degrees only for our convenience. We are converting angle from radians to degrees. But practically, see, all electrical signals will produce radians angle only. Clear? So these are all the results. This is about the output speed, torque generated by the machine, flux. This is about current. If you observe the flux waveform throughout the operation, it is maintaining constant, right? So at exact t equal to 0.5 second, load is applied on the shaft, right? Suddenly load is applied here, right? Next, at exact t equal to 0.8 second, load is removed. Even if you apply the load torque, or even if you apply the remove the load, if you observe the flux, there is no effect on the flux. If your controller, DTC controller, is working fine, how we can justify if there is any change in the speed or if there is any change in the load, flux should not get effect. Nothing but torque and flux must be independent to each other, right? So here flux is completely independent of the torque. Torque is also independent of the flux. Because of this reason, we can conclude that torque and flux are controlled independently by using proper voltage vector. By selecting the proper voltage vector in particular sample, independent control is possible. Clear? Understood? Next, what are the limitation here? What is the issue? Advantage is control circuit is simple, transformations are not required. Next, inverter switching frequency is variable, less, okay, no problem for drives application. We no need to bother about the switching frequency. This is also fine. In general, for low and medium power application, they will adopt. But what are the limitation here? Torque triple is high. Okay, very good. Any other issues? Any other issues here? There is a issue, serious issue is there here. So by adopting the DTC, we can eliminate the transformations. We can eliminate the transformations are not required, right? Your control circuit become very simple. Orientation is not required. We no need to bother about orientation. Field orientation is not required. Only field position is required. That is sufficient. Main issue is torque ripple. Reason why torque ripple is more. Even if you take PA controller also same. See, issue is here, even if you take FOC or DTC, right? Whatever voltage vector, see at T equal to kth instant, flux state is +1, torque state is +1, right? If sector number is 1, S equal to 1, sector number 1 is 1. So what is the required voltage vector in sector 1 to accelerate the torque and flux? What is the required voltage vector we are selecting? V2, right? This V2, this one, everything we are doing in particular sample period. Calculations are doing in sample period. Let us assume that, see, in particular sample period, what we are doing is at kth instant, we are calculating what is the error, what is the state of the flux, right? What is the state of the torque, whether it is 1, +1 or -1 or 0 we are calculating. Then what is the sector number of the position. Based on this one, we are executing the switching state and we are getting the what is the voltage vector is required. To minimize these variables, we are identifying. But issue is whatever voltage you are selecting at kth instant, whatever voltage you are identify to rectify the error at kth instant, this voltage vector we are not going to apply at the same instant. We are applying next instant. You got my point? We are applying next instant. This vector, we are applying this vector at k plus 1 instant. But thing is, at k plus 1 instant, error may different. Flux error may change. Torque error also may change. So whatever voltage vector we are applying at k plus 1 instant, that voltage vector will not satisfy the signals, will not satisfy the error 100%. Whatever voltage is applied at k plus 1, that voltage is 100%, it can satisfy the error at kth instant. But we are applying at k plus 1 instant. That is the issue. So because of this reason, ripple will increase. This is happening in all controllers, hysteresis controller, PA controller. This is the main motivation behind the model predictive control method. In model predictive control method, what we are doing is at kth instant, we are calculating what is the characteristics of the error, right, at k plus 1. See, in model predictive controller, what we are doing is at current instant, we are calculating flux error, flux state. What is the nature of the flux state in coming sample? What is the nature of the torque state for the next instant? So what is the required voltage vector for next instant? They will predefine, right? This voltage vector they will apply at k plus 1. Whatever voltage they are selecting for k plus 1 instant, that voltage is 100% responsible. It will take. That is the logic behind model predictive control. That is the basic difference between conventional control and model predictive. Nothing is there. But thing is, you have to follow some philosophy. Yeah, there is a methodology is there. If you follow that methodology, we can easily adopt this concept and we can minimize the error. We can minimize the whatever error is, whatever ripples are there because of this sample delay, right? Delay in the sample. Because of delay in the sample, whatever voltage, what is the difference between the
previous sample and current sample voltage vector, there is a one sample delay is there, right? Because of this one sample delay over the period, if you verify the response, definitely it will, there are a lot of ripples are there because of this one sample delay. That's why later they have proposed a lot of methods to eliminate the effect. So say with respect to power converter side, they have proposed hysteresis controller, linear controller. Under linear controller, right, field orientation control, PI based control, sliding mode control, predictive control, artificial intelligence, right? Next, under predictive controller, this model predictive controller become very popular, right? So what is model predictive controller, we'll try to discuss in detail. So these are all the applications of the model predictive controller. Initially this model predictive controller they were adopting in chemical industries. Later, right, why chemical industry they adopted this model predictive controller? Preciseness. Okay, see whenever they want to test some chemical reaction, it will take some time, right? See, at particular time, what they will do, see, by using this model predictive controller, they will predict how chemicals will react after 10 instants or 20 instants. They will take horizon of the controller, right? Clear? This is very important in chemical industry application. Selecting the horizon is very, very important, right? How system is responding after 10 cycles or 20 cycles are so important. For drives application, 1 instant or 2 instant, how, if you know how system is respond, it is fine. In drives application, we are taking only one sample ahead. We are going to take horizon of the prediction is only k plus 1 instant. But chemical industry, they will take k plus n samples, right? They will predict the system response at k plus n sample. More period prediction is required for chemical industry. For drives application, what is the nature of current, what is the nature of flux, what is the nature of torque? If you know at k plus 1 instant, in future, just future step, we can control the error effectively, right? So if you want, particularly if you whenever if you want to adopt this model predictive control method, this is very essential. Without knowing the, see, what is the advantage of present days? Tell me. Next, one more important thing is this model predictive controller, right? We cannot implement in analog system. Using analog controller, we cannot implement this. See, whenever you want to adopt model predictive controller, your controller must be in digital platform. This logic we can implement only for, if if it is a digital controller, we can easily adopt. With analog controller, it is not possible, right? Model predictive controller is applicable only for digital controllers. Now, see, there are two things are there. Tell me, what are there two things? Observe. What is there on right side? What is there on left side? There are two things. One, particularly one side, right side. What is there? What is there on right side? What is here? This is controller, right? What is there on left side? Power converter and drives, right? Now, what is the advantage of the current technology? Our technology is so matured for mathematical wise also. For each case, for each system, there is a approximate mathematical model is available for each system. Even if you take PMSM, IPMSM, surface PMSM machine, or synchronous, induction motor, SRM, synchronous reluctance motor, whatever machine you want to take, you can take. We have sufficient mathematical model, approximate model we have. Mathematically, we have support for each and every system. That is one advantage, right? Next, one more important thing is power electronic side. What is the advantage? What is the advantage? We can easily predict once you're having power circuit diagram of the particular system, power converter, we can easily predict what is the position of resultant voltage vector for particular switching state. We can easily calculate. If it is a multi-level inverter or two-level inverter, see, whenever you want to identify the resultant voltage for particular switching state, right, it is very easy to calculate. if you know the power circuit, and if you know the how many switching states are available for particular power converter, we can easily predict switching states, right? With respect to converter side, we can easily calculate what is the resultant voltage vector. Next, come to with respect to drive side, we have enough mathematical model support for each system. Now come to control circuit side. Control circuit side, then tell me, we have digital controllers. High-end processors are available nowadays. We no need to bother, right? By doing parallel operation, same logic we can execute with less time. You got my point? Even though your program is very lengthy, by taking parallel operation, right, we can execute the same logic with less time. There is a lot of advanced technologies available on the control system side. Drive side, mentally it is very matured. All electrical machines have sufficient electrical equivalent models. Electrical circuit models are available. Next, power converter side, we can easily, if you know the switching states, we can easily identify what is the resultant voltage vector produced by the power converter. Also we can identify, right? By taking the combination of advantage of the advanced digital controller, and by taking the advantage of machine modeling, and by taking the advantage of switching states of the inverter, we can easily implement model predictive control. If you want to implement model predictive controller, important thing is you should know your machine model equivalent circuit diagram. Without knowing the machine model equivalent circuit diagram, or without knowing the characteristics of the machine, we cannot develop the machine model. We cannot develop the modeling. Model predictive controller. Model predictive controller, name itself will represent model predictive control. If you want control, you have to go for predictive. If you want predictive something, you should know mathematical model. That is the method philosophy behind the model predictive control. You got my point? MPC, model predictive control. Objective is control. If you want control, you have to go for prediction. By predicting the variables, control variables, we can apply accurate voltage vector for particular sample period. But if you want to predict what it required, model is required. Yeah, previous data, current data is required. Based on the current data, we have to predict the information, right? So here this is about this equivalent circuit diagram of the standard equivalent circuit diagram of the model predictive control. You can apply, you can take as a, right, grid connector inverter also you can take motor load. This is generalized block diagram common for any system, electrical system, right? So here in model predictive control, important thing is, what is the advantage of model predictive control compared to PA? What is the limitation of the PA controller? Saturation, tuning already we discussed. Everything we discussed. Tuning, huh? What is the problem with PA controller? PA controller is applicable to control only one input and one output variable. It is, if you take PA controller, maximum how many variables we can insert? One. How many maximum? See, PA controller will give only one control variable. For single input and single output, PA controller is applicable. But the beauty of model predictive control is we can give multi inputs to the system, multi variables. You can give multi input and multi output mechanism. You can go for model predictive control. You can give n number of inputs and you can expect n number of outputs also. We can extract n number of control variables also. That is the strength of model predictive controller. This is basically it is a non-linear control method, right? It is a iterative method. It is a non-linear method, right? PA controller is a linear controller, but model predictive controller basically it is a non-linear controller. Non-linear and iterative process, right? So that finally, if you want to iterate something, it requires cost function, right? Right? This is a very important thing is this one. If you take PA controller, it is nothing but only single input and single output. But if you take model P2 controller, right, it will process multi inputs and multi output signals. So this is the basic difference between MPC and PID controllers, right? So this is about predictive control. First you have to define cost function. What is cost function? Anyone? See, if you understand some key points, it doesn't require more time to understand the philosophy behind this logic. What is cost function? Anyone? In cost function, we need to take error of the target variables. See, in PA controller, what we are doing? What is the input to the PA controller? What is the input to the PA controller? Error. Here also cost function we are taking. See, in PA controller, we are taking error of the control variables, target variables. Torque error we are taking. Speed error we are taking. If you want to control the speed, your PA controller will give how much torque we need to maintain. It will calculate and it will give information to the controller. Then again, if you compare reference torque with the actual torque, then again if there is any torque error is there sent through the PA controller, what it will do is torque controller will give how much voltage we need to apply across motor terminal. Your torque controller will decide. Right? In model predictive control also, in cost function, please start understand. Model predictive controller is a multi-input and multi-output system. Right? So in a simple, by taking single equation, we can calculate, right, what is the required voltage. By iterating process, we can identify what is the optimal voltage vector is required for next sample period. Which voltage vector is working effectively in the next sample period, we can predict by taking the cost function. Cost function contain the errors of the target variables. What are the target variables for electric drive? Torque error, and our target variables are torque and flux. In cost function, there are two. Initially, we'll calculate first torque error and flux error. Right? At what switching states this error will minimize, right, based on the available switching states of the inverter. There are 8 switching states are available for 3-phase 2-level voltage source inverter. If you iterate this cost function with 8 voltage vectors, after completion of the switching instant, after completion of the sample instant, you will get optimal voltage vector. If you apply that voltage vector in next sample, what will happen? Advantage is your error will control effectively. In cost function, we are taking error. This is about, see, there is a, if you take here, this is the mathematical model for cost function for electric drive. Suppose if you want to develop grid connector inverter, their requirement is, what is their target in grid connector inverter application? Suppose for power quality improvement application, their requirement is real and reactive power control. Whenever you want to control the real and reactive power, in cost function you have to take control variables. Real power error you have to calculate, reactive power error you have to calculate. See, important thing is here we are not calculating the error at current instant. So here this is the important thing is before calculating the cost function, this is the very crucial. What is this 2? This cost function we are calculating at kth instant. But see, but if you observe the cost function equation, we are calculating the error for future state, next instant. Right? How we can calculate T of k plus 1? This is through mathematical model. Once you know the characteristic equation of the particular system, we can easily predict what is the torque generated by the machine based on the current state, current instant, current torque, everything. At particular instant, what is the current drawn by the machine, what is the flux generated by the machine based on the current drawn by the machine and based on the flux generated by the machine at kth instant, we can easily predict what is the torque, what is the expected torque in the next sample period, we can predict. Right? Similarly, how we can predict flux based on the current. You got my point? These all are mathematics only. By using mathematics, we can able to predict behavior of the actual torque in the next instant, behavior of the flux in the next instant. We can predict and calculate error Next here issue is what about this one? What about lambda? This is called weighting factor. What is weighting factor? You need to select the weighting factor. You need to take care about this weighting factor such that we can balance the units. Here, what are the units for torque? Units of the torque error and units of the flux error are different. Units are different. If units are different, you should not write in common platform. Right? So, if lambda equal to, suppose if lambda equal to torque by rated flux, if you take lambda equal to rated torque by rated flux, or rated torque by rated flux, then what will happen here? So flux will cancel. Finally, this component unit become newtons only. You got my point? You need to take base value. By taking care about the lambda weighting factor, right? We can balance the units. Next, one more important thing is the selection of lambda is also so crucial based on your priority. Right? Based on your priority, you have to adjust the lambda. Suppose your top priority is flux controller, you have to take lambda very less. If top priority is flux controller, you have to take lambda more. By adjusting the lambda value, we can control the priority of the target variables. But in electric drive, our primary objective is torque. That's why lambda they will take very, very less, so that by taking less, by giving less priority for flux controller, automatically torque will control more effectively compared to flux control. Right? So that, right, here this all are mathematics. So this is the mathematical universal voltage expression. Right? This is about rotor flux equation, stator flux equation. By using this standard mathematical model of the equation, if you know the current information, flux information at kth sample, right? We can easily predict what the flux generated by the machine in the next instant. We can predict based on machine modeling equations only, right? See, once you know the flux information, right, later we can see this is the mathematical model for prediction of the stator flux, right? Once you know flux and current, prediction flux and prediction current, then by using this equation we can calculate prediction torque. So once you know the prediction torque and prediction flux, we can easily calculate. This is about mathematical model for weighting factor. By choosing this weighting factor, they will decide based on the rating of the machine. Without knowing the rating of the machine, it is very difficult to decide. But researchers, while doing their research, what they will do is they will do trial and error. By doing trial and error also, we can select the lambda based on the performance of the machine. By selecting the lambda, we can see performance is good, fine. You can select according to that value, right? Next here, this is about inverter switching state. There are 8 switching states are there, right? Your job is for each switching states in a particular sample period, in particular sample kth instant, your job is you need to calculate what is the cost function value for V0 and V7, V1, V2, V3 for with available voltage vectors. You have to iterate the cost function. So finally you will get information in particular sample period. You will get complete information about complete profile. This is about profile of the cost function, right? How cost function is regulating by changing the switching states, you will get information. If cost function is more, error is more or less. Cost function is more, error is more or less. Cost function is more, error is more. You should not select that particular voltage vector. See here, after applying these 8 switching states, if you observe this one, V2 it is producing less cost function. Your cost function becomes very, very less if you select V2, right? So this is, so finally, right, this is the where V2 is the optimal voltage vector. It is called optimal voltage vector or predictive voltage vector for next sample. If you apply V2 for next instant, definitely your error will come down compared to other control methods. PI controllers or hysteresis controller or other controller, right? Even if you take fuzzy logic also, compared to other artificial intelligence methods or optimization methods, this model predictor also, it is optimization. It is like optimization compared to all other methods. Here we can improve the profile. See here, you can observe this one. Focus on this current waveform, right? This is a current instant, right? If you select V2, this is the change in the current. If you select V2 or V6, this is the position of the current. If you select this one, right, this is our reference. This is about our reference current. This is the actual current. So at kth instant, what we are doing is we are predicting which voltage vector will produce minimum current error. We can calculate, right, based on the predefined calculation. So out of this 8 voltage vectors, V2 and V6 voltage vector, if you select, actual system will come closely to reference. This is the error. So error become very less, right, if you select V2 voltage vector. That is the advantage if you adopt model predictor control method. This slide will give see comparison between PI controller and model predictor controller. See, in PI controller, what is happening at t equal to kth instant, what we are doing is we are calculating the error. Whenever you want to calculate error, you need to take information from the previous sample. Everything you have to get from the previous sample, right? Whatever information is coming from the previous sample, it will not give sufficient response. But here we are at kth instant, we are predicting what is the voltage vector for next sample period. We are predicting, and that voltage vector, if you apply in the next sample, your error will come down, right? So this is about results of the DTC and MPC case. If you observe the torque generated by the DTC and torque produced by the MPC method. This is one of the method under MPC method. This is called predictive torque control method, right? Now you can observe what is the advantage of PTC. Observe steady state response. Both are same or different? Ripples are less. Why ripples are less? We are calculating the required voltage vector one sample ahead, right? Whatever voltage vector is selecting here in hysteresis controller, that voltage is not really control the current state error. Current state error is different. Applied voltage vector is responsible for previous sample instant, right? So that is the issue with the DTC. That's why ripples, steady state ripples, we can minimize by adopting the MPC. One more important thing is, by using MPC, we cannot improve the dynamic response. Compared to MPC method, DTC method dynamic response is very good, but deviation between the DTC and MPC is not that much, right? So by adopting the MPC, we can improve the steady state. Many of the scholars, they are focusing is on improve the steady state performance, right? If you want to improve the steady state performance, all are vector control only, DTC, MPC, field orientation, right? So you no need to bother about the dynamic response. Your job is, your primary objective is, you need to take care about the steady state response, right? So even if you want if you want to improve the carbon mode voltage, you can add one more objective, one more objective in cost function. You can add n number of objectives in cost function, no issue. But problem is, you need to take care about the priority. See, there are 4 objectives are there, right? What is the priority of the first objective? What is the priority of the second objective? Priority you have to decide. After deciding the priority of the cost function, control objectives, then what will happen? According to that, your controller will select, your model predictor controller will select optimal voltage vector. The selection of voltage vector is based on your priority of the control variable, right? See here, suppose if you want minimize further, your objective is not only control the torque and flux, further if you want minimize the switching frequency, you can add switching frequency constraint. Otherwise, if you want to improve the common mode voltage further, you can add common mode voltage also. You can add common mode in cost function. Next, reactive power reduction. If you want taking care about the reactive power reduction, you can add. Based on your requirement, you can taking care about this one. Cost, more number of variables, more number of control objectives we can include in the cost function, and number of objectives we can add. It is not like simple single input or single output. You can add n multi inputs and multi outputs you can express. So what are the challenges in MPC method? What is the big challenging? What is the main issue? Number of calculations are more. That's why nowadays there is a lot of research is going on to minimize the parameter sensitivity in the prediction. Right? To see here, while if you want to predict the torque profile or flux profile, right, it requires a lot of machine equations are required. Right? So if you once prediction is depends on the machine equations, then these parameters may change based on the operating conditions. So whatever you are predicting the torque and flux, it will not give accurate value. That's why without model also they are trying to predict the torque profile as well as flux profile. There are a lot of research papers are there. If you want, you can go through it. Right? Next, tuning of the weighting factor is also very important. That's why what they are doing is torque and flux, they will convert it in terms of current. Once torque profile and current profile are in terms of amps, you don't need to take weighting factor. You got my point? If you take torque and flux independently, directly, right, it required units are different. Otherwise, if you express torque in terms of current as well as flux in terms of current, then finally, if you take ID and IQ, what is the advantage? Torque control variable, flux control variable, both units are in terms of amps only. In that case, if both units are same, you no need to go for weighting factor. We can eliminate weighting factor. That's why it required transformations. Whenever you want to eliminate the weighting factor, without taking transformations, we cannot eliminate the weighting factor. Right? Shall I stop here? Anyone having doubt up to here? Now clear. I think till now, see, particularly in this session workshop, I see my objective is what is the control point of view, control of the electric drive. That is my objective, right? Another professor main objective is design part, design controller, right? Then after that, see, whenever you want to control, you should know actual system characteristics, right? So we discuss initially we discuss how to extract the actual system characteristics based on the torque profile we discuss. After that, what is the need of transformation we discuss, what is the significance of transformation, right? Particularly while converting the three-phase to two-phase transformation, right? What is the advantage with respect to three-phase system we discussed in the last class. After that, field orientation, DTC, MPC we discuss in detail. Next, anything is missing according to our lecture schedule? Anything is missing? Check. I think we covered whatever topics we mentioned in the lecture schedule. I think we covered all, right? We have not skipped any topic. We discussed more than what we presented in the lecture schedule. Fine. Thank you. Thank you very much. Observe carefully what is the nature of air gap flux, magnetizing flux. what is the nature of, you forget about transient condition, this one. Under steady state condition, what is the nature of magnetizing flux? It is not ellipse. Scale is different. That's why it is. Don't think it is ellipse. If it is ellipse, no use. Everything gone. Whatever we discussed till now, everything gone. It is not ellipse. You can check y-axis and x-axis, diameter. It is circle on. Otherwise, it is not. Fine. Now it is fine. Is it circle or ellipse? It is circle only. Now, see, instead of starting the sector number from 360 to 330 to 30 degrees sector 1, if you take 0 to 60, then you can observe, see, you can notice what is the here 0 degrees to 60, 60 to 120, 120 to how much? 180, 180 to 240, 240 to 300. Fine. 360 same. We no need to worry, right? Clear? Then we'll check what is the nature of magnetizing flux. If you start sector number from 0 degrees, then you can see here, you can check. Is it wanted or unwanted waveform? This is unwanted. Magnetizing flux should be rotating in circle. The nature of magnetizing flux should be alternating in nature, circle shape. Then only we can produce unidirectional torque. This is very important. If you want to produce unidirectional torque, your magnetizing flux should be sinusoidal. Your magnetizing flux must be rotating in circle. If you start your sector number from 0, right? This is the nature of magnetizing flux, right? If magnetizing flux is like this, you can check your flux, your torque profile. Where is a torque profile? See here. You can check. There are a lot of ripples are there in the torque. This is the torque response. There are spikes are there, right? Spikes very dangerous. These spikes, right? See. Next, one more important thing is many scholars, they are thinking about, see, based on the torque ripple, our speed will get effect. See, based on the density of the torque ripple, our speed vibrations will affect. You got my point? What is density? Flux ripples are there, or torque ripples. If there are any ripples are there in the torque, I will show waveform so that you will get clarity. You will get more clarity about this one. So before wind up the today's session, right, after this point, I will conclude the session. Right, there are two things are there. This is case 1, case 2. In case 1, torque ripple, this is about torque ripple. Right, +1 to -1. In case 2, ripples are +2 to -2, but frequency is more. Ripple frequency is more. In which case your speed will get effect? Ripple is more, but ripple frequency is very good. In which case your speed will get more effect, case 1 or case 2? In case 1 your speed will oscillate more. Even though ripple magnitude is less, but ripple frequency is very poor. You got my point? I will tell example. Take needle, press here, right? Even though pressure is very less, if you maintain more period, you will get pain, you will feel pain. Otherwise, even if you press more and remove immediately, you will not feel any pain, right? You got my point? See, less this one, less pressure, more period, your system will get effect. Even if you press more with short period, nothing will get effect. So many of the scholars, they are thinking that my ripples are decreasing, my performance is very good. Don't think. Even ripples are decreases, you need to take care about the ripple frequency. Ripple frequency is more, even magnitude is more, ripple frequency is more, your system will not respond. If ripple frequency is less, magnitude, even though magnitude is less, ripple frequency is very poor, time period is more, then definitely your speed will get effect. You need to take care about the ripple frequency also. Ripple frequency and ripple magnitude, these two are very important factors, right, to protect the bearings of the system. Bearing cost is very expensive. It is 20 to 25% of the initial cost of the machine. That's why if ripples are more in the torque, it will reflect on the bearings, right? Okay, thank you very much. See, assignments, about assignments, see, today night